We've got half an hour for this. I'm told we have to stop like a couple of minutes just before 2 o'clock, before the next session starts downstairs, to give us time to go downstairs and find our seats downstairs as well. Welcome to this first lunchtime session at this conference. I was asked by you to chair this very interesting looking session. I'm not going to spend much time talking because we have limited time. 10 minutes for each speaker, and then there's some time after each speaker for some questions from the floor. The first speaker is Ian Simpson. He is a university technician and by trade, and became aware of climate engineering around 2012. He's of the opinion that there are multiple climate engineering programs already underway on a global scale. And I believe your primary interest is in dispersal systems on Airbus aircraft and Boeing aircraft, and some of the global infrastructure which you say is necessary for this climate engineering program. So I'm going to hand over to you.
Hello everyone, thank you guys for letting me talk. We've only got 15 minutes, so I'm going to try and talk quite fast and just rattle my figures. Everything I talk about is on my website, so please do look it up. That's the web address there. Basically, we've got this smokers video I'm just going to show you, which I filmed some time ago, and this is what I would, we're jumping straight into the deep end here, this is what I would call probably the world's most incontrovertible evidence that planes, aircraft are spraying something into our sky. We see thick black smoke coming from a fleet of planes that were not listed on any website, no flight radar. The CAA deny all knowledge of them. They are commercially liveried A320 jets flying in circular patterns, up and down, doing U-turns. And when you look at the plume, basically, we spoke to Rolls-Royce about this, and their engines are absolutely super clean. There's no atmospheric condition or engine malfunction or anything that can produce that, basically. The video is about 10 minutes long. We'll try and skip through it. And then when you look at the pattern on some of the plumes as well, we see characteristics, as in here, basically, that are consistent with 3-pipe aerosol delivery system. So the top 2 pipes are basically spraying a constant stream. The lower pipe is a pulse ejection system. Funny enough, I'm going to stop this video now and go to the presentation. Okay, I'll just flip through those. We see a lot of similarities, basically, between the things that we see and the predicted things that we are supposed to see with the proposed programs as described by many of the world's leading scientists, and we also see similarities in the equipment proposed and the equipment that we have discovered exists on aircraft currently. Airbus have stated categorically in writing and a recorded telephone conversation to us, their planes, their A320s, do not leave the factory with any pylon pipes. Okay. Essentially, planes never used to make clouds. Really, that should be end of story. Sadly, it's not. So we find ourselves in a quagmire of trying to explain all sorts of things to scientists that we know nothing about. And I likened it to entering the Vatican and telling them God doesn't exist. It's a difficult situation, but we are getting there. I'm going to crack on with the 3 primary programs that I've identified today. Persistent spreading trails, anyone who doubts, basically anyone who's trying to do climate engineering knows all about persistent spreading trails, and that's pretty much what most people talk about. But there are 2 other basic programs, which are smokers and hazers, which I'll focus on today. Smokers, we saw the video. What's going on? The only explanation we can think of really is that the 3-pipe aerosol delivery systems, which are generally used for the persistent spreading trails, are being used to pump diesel into the atmosphere or some kind of fossil fuel. Why on earth do they do that? Simple, 400 parts per million, fear. This is what they're trying to do. They're trying to raise CO2. They're pumping loads of smoke into the atmosphere. It has detrimental health effects I don't have time to go into now, but essentially it's all about creating a climate emergency on the back of which they can create a state of emergency on the back of which they can do anything they want. I won't go into who they are. You've seen the video. This could be, we don't know, we've not managed to get any samples, we've not managed to do any testing on it, but Greenland ice is covered in black soot. Where is it coming from? Could be fires, it could not be. But you know, when you see videos of planes pumping fossil fuels into the sky, it makes you wonder. Second programme, haze. I work in theatres. If you want to create a nice hazy environment, what do? You get what's called a cracked oil machine. What does it do? It pumps tiny little particles into the air, and all the lights seem nice and fuzzy and beautiful. That's what our sun looks like on most days these days. Haze pipes, these are 737-800s. This is not my image, all the other images are all mine. This was taken from the internet. The 737-800s have a very different system. Firstly, the containers are on the rear of the aircraft, on the front, and it's a single pipe. You don't need to mix anything for this stuff. They're basically tiny little plastic fibres, and they fill our skies on most days. This is probably the hardest bit for anyone to accept. To most people, they would say, this is what our skies used to look like. This is a beautiful natural sky. Wrong. Okay, this is what I call induced cumulus. Now, if you pump trillions and trillions of tiny little fibres into the atmosphere, and we think they're around about 2 to 20 microns, what's going to happen? On days of high moisture, they will form clouds. And basically, the pattern with which these clouds emerge shows that they're not really forming naturally. They're not coming in great big banks of clouds. What you will see is a deeply hazy sky in the morning, every morning. By lunchtime, you see tiny little wispy bits appearing, and they get bigger and bigger and bigger, and then suddenly uniformly all over vast areas, we have these little fluffy clouds. They're never very high. In terms of high moisture, they can get bigger. Otherwise, if there's very low moisture, you just end up with a hazy, filthy mess. Okay. Ultimately, I can't prove anything here today, you know. And again, you know, I'm talking to some clever people. But ultimately, I'm hoping that some of you, it may see this little down, and you might take it away and run with it. So, you know, everything here can be explained with, oh, it's probably just. But, you know, you're scientists, that's not good enough. Prove me wrong, please. These are the fibres under a domestic microscope. This is, actually, I'll get onto that in a second. We've got, this is some of the fibres under an electron. We've also done mass spectrometry on them, and it seems they're basically a form of plastic, some kind of polymer plastic. We're not quite sure yet. We're trying to get those results out for Berlin. I'm going to do, hopefully, trying to do a big talk in Berlin where we present all the scientific evidence behind this and go a lot deeper into every aspect. Where it gets really disturbing is this stuff collects in your throat. Okay, on our tongue we have collections of these little fibres. What they do, we don't know. We don't know how they basically assemble, why they stick into our throat. These are the desiccated samples. This is what they look like when you dry them out. We have like a vascular structure. Again, plastic. If you burn them, they're plastic. Okay, persistent spreading trails. You know, most of you know all about those. But what we're going to do is prove that they're coming from aircraft, hopefully. What we've been doing is looking at the formation of these trails. This is quite a good image because it shows loads of different trail types. This stuff here is a particular chemical that's generally sprayed to induce rainfall. We always see it. The Met Office invented a bunch of new clouds a couple of years ago, or in the last 2 years, and Umpenus was one of them, along with Halo and you know a load of other stupid names as well. That they just invented out of nowhere and put up on their website. Umpenus is one of them. We don't know what these chemicals are. We can't, you know, I can't go up there and take a sample. We can take atmospheric samples, but then people go, oh, it could be from anywhere. It could be, you know, cars or industry or stuff like that. So you know, we're in a very difficult position, but we're getting there. There, smoking guns. Airbus A320s, these are the pipes. You can even see, if we zoom in, this is the best image we have so far. Okay, the metalwork's been cut away, 3 pipes. Top 2, constant stream, the bottom one we believe to be the pulse. Okay, the pulse produces little puffs of smoke. When you see these trails spread, you have 2 lines in the trail, you have little puffs underneath. The puffs form the bobbling cloud forms a very thin layer, and you know, it goes on and on and on. Oh wow! 3 planes in one sky, all the same altitude, one with a trail, 2 without. How do you explain that? This is another one that I invite scientists to disprove. Look at, so we're talking about 2 to 3 meters, okay, to drop from 900 degrees centigrade general operating temperature of a jet in cruising speed, and the formation of so-called ice crystals. If you work it out, it's about 0.2 to 0.4 milliseconds. Is that possible? Minus 57 degrees from 900? I don't know, you tell me. Seems suspicious to me. Different trails, one comes from one comes from another, different chemicals obviously, different substances. Different trails again, you see two different trails from the outside ones to the inside ones. Combination therapy, we often see two jet planes travelling in parallel right the way across the sky. One will be leading a short, hazy trail, the other will be leading a very thin, persistent trail. They seem to mix, they seem to be doing something. We don't know what, again, you know, we can only point them out. Various other things, we're looking for clues, we see patterns in rainfall, in respiratory diseases, in aircraft patterns, where they fly and in what quantity seems to relate very directly to respiratory problems, to rainfall, all sorts of things. Here's a great one, 635, 741, okay? You counted about a dozen trails there. That's what planes can do to the sky. If you can't see all this, you're being paid too much. That's my little saying, basically. New clouds, Kravitz is basically the persistent trails in high moisture. What they do, they form these little wobbly things. In high moisture, they drop. They don't actually generally tend to rain. The implements seem to cause the rain. Various other things, aerotoxic syndrome, haven't got time to go into. Blah, blah, blah. I'm going to stop there and go on to questions because I don't really want to take up any more time. So again, you know, I do talks on this publicly, and I'm quite willing to come back. My talks are generally 3 hours with another hour discussion. So if you really want to know the nuts and bolts of what's going on and go into depth, then I'm quite happy to do it. If not, you know, I can wait till Berlin if they let us talk. So any questions?
That's very smart. 10-minute talk from you. Are there any questions people would like to pose?
Yes.
Are there any theories about who's doing it?
Yeah, it's not something I like to go into because it's very, very difficult to prove. But essentially, one thing you need to consider is there is no such thing as a national airline anymore. Virtually all airlines, apart from some of the UK budget ones and European budget ones, belong to 3 airline alliances, and they've all been amalgamated over the last 20 years. And when you look at the corporate structure above the directorship level, then you're talking global billionaires, basically. So, why? Well, do you know what? Why do people rob banks? When you see people robbing a bank, you don't go, oh, why are they doing that? You know, you just phone the police. I don't know. Well, I do know, I have my own theories, but it's not something I get into, basically. My focus is basically saying, look, see that shouldn't be happening, can you do something? So, yes.
There's a question at the back. You?
Yes, sir. Yeah, my engineering colleagues here, I've shown them your leaflets, and various people have said, well, that sounds very interesting, and have gone away and proposed different things they might be. One being that it's really important, given that the wings of an aircraft are also the fuel tanks, it's very important that you have ventilation of the various spars on the wings, and that different airlines and different aircraft use different means of ventilating the spars. And these are, according to my colleagues, spar vents. Do you know if that
well,
really is?
Yeah, I'll answer that. Basically, we spoke to the ARSA, and they have no explanation, basically. They have no license for this modification. All aircraft in Europe are covered by ARSA. Any modification is either a major or minor modification, requires a license. They have no record of the license. Also, Airbus said they're not original. And we've spoken to chief engineers of various airlines, and they've come up with all sorts of ludicrous excuses about moisture release and hydraulic release, even fuel dump pipes. I mean, dumping fuel into a 900C exhaust drag plane. You know, so we can't prove it yet. We're basically launching legal action very soon, and we're going to get Airbus in court, and we're going to make them tell us exactly what it's like. That's really where we're going. But we would like some scientific evidence to back this up as well. Because ultimately, we believe that at least some of these programs could be harmful. I can't say more than that at the moment. I'm not one that goes, look, they're killing us. But, you know, I'm very suspicious.
Chap at the back, if you'd like to say who you are, not like it up.
Yeah, sure. David Bowen, Cambridge. I just had a question on your Fraile-Martin, the Fraile-Martin theory behind the exhaust engines. So you're aware that most Rolls-Royce engines run at about a 92% bypass rate? So
no, I have absolutely no idea what that means.
Okay, well,
I'm not an engineer.
Sure. Okay. Well, I think perhaps you might like to ask an aircraft engineer why you get that 3-minute separation, because a Rolls-Royce engine runs at about a 92% bypass rate. So essentially, what you get is a mixing of the exhaust gases with the minus 50-degree gases as they come through the engine. So essentially, you've got your standard jet engine going.
Well, that's only the case on a turbofan engine, isn't it?
But that is a turbofan engine that you put up there, right?
Okay.
But they're all turbofans, so you get mixing of the exhaust. So what you
They're not all
don't
turbofans, but anyway.
Sorry?
They're not all turbofans. Some of the old
That one you put up is a
7,800s are not.
turbofan. What you put up there is a turbofan.
Right, no, that's a valid point. I mean, I did say that, you know, that's not something I've gone into. I haven't had time to research it, so if you can
Should we
share
just, we just let the
tell the public, if you don't tell the public that it's impossible for there to be a 3 metre gap.
I've not said that.
But I mean, that was what you tried to put forward to us. You sort of need to check with somebody who actually knows about this stuff. Similarly with the pipes, right? Ask somebody who put the pipes on the aircraft rather than
Well,
just
put
saying,
them on then.
oh, we checked with someone and nobody quite knows where they came from. If you ask an aircraft engineer, they will be able to tell you where the pipes came from, right? The pipes there for a reason.
Well, we spoke to one engineer and he said it's nonsense. There's no such thing as a requirement pipe. Okay, off the record.
Sound like a very broad
On the
statement.
record, basically, they say they're original. Rob Crew, I spoke to Rob Crew, Chief Engineer at British Airways. Oh no, they're original, we haven't modified our planes. Airbus claim different. So who's telling the truth? You know, EasyJet, Chief Engineer, I've got it in writing, they're hot air vent pipes. Rolls-Royce said, we don't have hot air vent pipes.
But
It's actually not coming out through the pilot. So
the engine.
who's telling the truth?
The vent pipes from the wing, not the engine. So you don't go to an engine manufacturer asking why they've got vent pipes from the wing.
So you're telling me one of the chief engineers at Rolls-Royce doesn't know what he's talking about?
Well, the chief engineer of Rolls-Royce is designing the engine, not the wing.
Yeah, but you should know where all the pipes go.
Okay, let's move on to the next question. Piers?
Piers Forster. I had a question. So, for my job, I'm an atmospheric physicist that has done a lot of work on contrails, and I'm very, very, very confident I can explain all the picture you have shown me today as just contrail. So, do you think I'm part of that conspiracy?
No, because I don't know you and I don't know what you've got to say, but I'd like to talk to you, yeah. I'd like to hear your explanations. What do you consider the minimum conditions of contrail in terms of altitude and temperature? Because the Met Office used to say minus 57 degrees and 37,000 feet, which is the average temperature. The average height in New Zealand.
That is not right.
Well, no, I have it in an email, it is right.
Variable. It is variable.
Of course it is, depends. In a temperate zone, that's what they said.
That was an approximation anyway. But do you think I'm a scientist? I mean, what is it? There are 100 scientists like me that work on contrails. We're independent. So do you think we're just totally stupid, or do you think we are part of some conspiracy?
No, I don't judge anyone individually. As I said, my mission is to say, look, do you know what, actually, to me, that doesn't make sense. So I'm presenting my evidence, and if you want to come and talk to me and teach me something I don't know, I'd welcome that. You know, basically, when I see a plane at 16,000 feet leaving a persistent trail on a warm, sunny day, to me, that doesn't make sense. When you look at radiosonde data, you realise that you can't get those sort of temperatures, especially on a summer's day, to produce those kinds of trails. Okay, and then when you see another plane next to it, not leaving anything, to me that's suspicious. So come and talk to me, please. I'd love that.
We've got to press on with the next speaker now. We've got less than a quarter of an hour left. So, Josefina, Martin. Well, you'll use your time as best you can. Josefina is trained in physical science originally and is the president of the Association of Terra SOS Tennis, and a promoter and speaker, the international platform of Skyguards and yes, opposing climate manipulation. Plan to design aerial spraying in the frame of ongoing geoengineering programs. And she's going to tell us some more about that.
Well, thank you very much for being here. As presented is Josefina Fraile. I really would like to give a great presentation, but my English doesn't allow me to go as fast as the previous speaker. Okay, so I'll start this short intervention by explaining who we are, what we are not, and why we are here. Skywars is the civil society platform conformed of organizations from over 26 European countries. Skywars is an action platform born to address geoengineering and climate manipulation issues and to defend citizens' interests at all possible levels: research, educational, corporate, political, and legal. We are not climate change skeptics or climate change believers. We believe that the climate change debate is being distorted by vested political interests, with the result that what comes out is very much like propaganda. And this applies to both sides of the mainstream climate debate on climate change, believers and skeptics alike. You see, both are behaving in a very cynical way in our thoughts, and they would not consider in their studies the historical documentation. They don't consider in their research the impact on climate change of whether civil and whether military, weather modification and climate modification programs for over 60 years. So we are here to participate in this debate, to establish a direct contact with geoengineers, because we really have to overcome this situation. There is a gap between civil society and academic and scientific research, and we would like to express also our concerns to them, and we would like to point out what the previous speaker said, what we consider proof of or evidences of solar radiation management. We also wanted to address in this event some questions and demands to them, but I see that there is no time. So, concerning the first point, we see that the climate engineering and geoengineering is the most big issue after the atomic bomb, you know, that endangering the lives, the planet's survival. In spite of this fact, the debate is being confined to academic and scientific circles, and the controversial decision of intervening in the natural climate system is being taken at the backs of concerned millions of inhabitants of this world by people that are not legitimate to do it. In fact, geoengineers are claiming that legitimization on the grounds that extreme weather episodes, failure of CO2 mitigation measures, and in face of political institutions not backing up geoengineering programs openly for fear to pay the political price. Well, who is the legitimate? The legitimization is in the hands of citizens. Of course, elect our political representatives through convened electoral process. And based on this fact, there is no way that we, civil society, are going to recognize legitimacy to anyone not elected by us. So, and yes, we will make pay our politicians the price for having taken these decisions at our backs, and we will take them accountable for. So, we keep on with the second civil society representation. I don't know how this goes back. So, in a context of deliberate disregard for citizens over geoengineering, social scientists decided to become the interface between geoengineers and civil society, and arguing to themselves the representation of civil society. In this respect, we would really like to assert that we do not want to be represented by them. Civil society is mature enough to represent and defend its own interests. So I think the time has come really to rectify this undemocratic behavior and allow civil society to come to this debate as peers, to express their concerns, to express their experiences, and also listen to their theories. Okay, so it seems as if the Cambridge University is being the first one to give to rectify this behavior. We thank you very much, really, but next time we would like to have a place in the real agenda of interventions and not enough time sessions. So, this picture that you see, we do not work with modeling, we do not work with charts, we work with real life experiences. And we think that solar radiation management, weather modification, is like a pregnancy. You can only deny it for so long until facts are overridden, until arguments are overridden by facts, right? So, here are some facts. These are different places in Europe. So, geoengineers used to say that geoengineering is a hypothetical tool to cool the climate, but in any case, it will apply it when it needed without any field experimentation. And what we say is that actually the facts reported by citizens are that these programs are being really deployed widely open. So this is the result. What comes down, what is being sprayed up, it comes down. This is what it happens to nature. These are fibers that are being sprayed too. That's there. And this is our vision analytical data. We pass from taking soil samples in organic soil, and we pass from 5,600 milligrams per kilogram. In 1 year, we passed to almost 20,000, 19,300 milligrams per kilo. So also, titanium, we had passed from in 1 year from 0.23 milligrams per kilo to 1,500 milligrams per kilo. So this has an effect on these places where they are being sprayed. Our own research considers field observation data from Meteorological Association in Spain, satellite images with precisions, relative humidity to see if the trails are normal, that they could be really, you could see trails forming at a humidity of 40%. Wind saturation, cloud and water content. So this is how we explain it. This is what is happening. And now, this is Spain, and we see that all rainy fronts coming from the west side, coming through Galicia, San Jacobs, that part of Spain, and well, they are being spread right there in the Atlantic, and the rain doesn't come through the country. Okay, and these are the satellite images. Look how these clouds are being kept away from the mainland, and they have the shape around the shape of the country, right? And you see the shape of the country. Well, we have some questions. Do I have 1 minute? Okay, we have some questions. We know that these programs are being deployed under the protection or under the protocol of privileges and immunities of the United Nations. And we really wanted to ask you if you engineers are working under that protocol. The second question is, in spite of historical evidences of weather being used for military objectives since 1954, under the assumptions that the nation that controls the weather will control the world, military usage programs of weather warfare are left out of the equation by scientists involved in climate change debate. And we wanted to ask you why. So we have some more things to tell you, but we are now very much limited by the time. So please, if there are questions, thank you for your attention.
So it's on now.
It's on now.
Okay. Are we using a sensor?
Hi. I'd like to have a wander around the workshops in engineering, if that's possible.
Yes.
Yeah.
Yes. Certainly.
Yeah.
We've got lots of exciting experiments too. We've got lots of exciting demonstrations that I want to show you.
It's machine shops particularly I want to see.
Machine shops.
Yeah.
Are you going to be speaking again?
I'm supposed to be chairing this one.
Oh, are you? Okay. That's why your mic is going.
Yeah. This is live.
Fix your collar. Tuck it under your jacket. There you go.
Okay, good. Thanks. They're running terribly late upstairs. Could you get him mic'd up? Could you get the microphone for him?
He's got. Have you got?
Okay.
My friend really likes your book, Sustainable. I didn't read that book, so I don't really have much to say. But tell that what she wants to do here for this talk. So what other engineering I can do? Apart from Aerosol. No, I don't want to do that. No chemical engineering. I think people have bias view on manufacturing engineering. I talked to Tim and I asked him about manufacturing engineering. Tim was like, manufacturing engineering, seriously, the engineering? No, it's not. What's your view on manufacturing engineering? It seems like land economy, isn't it?
I'd like some advice about how long we delay the start.
Oh, we should be starting.
We should have started 10 minutes ago. But I'd like you to tell me when to go. People are still trickling in, but if they decide to go on the Science Festival. People are still trickling in, but it's slowing down. So you tell me when you want me to be.
Are you interested?
I'm the chairing of the next one.
I think we should just start.
Okay.
Yeah, down the front yet, do because my session's I'll still keep going. So, yes, the answer is yes. Sorry.
This is live now, is it?
Yeah, it is.
Could I ask you to sit down and get ready for the next session?
I think we should start now.
Okay. I'd like to introduce the next speaker, Professor David MacKay. He was doing physics here, and then he fell among civil servants, and he had really rather a difficult time there, I think. He didn't get time off for good behaviour, but now he's been released, and he's come back to being an engineer. And David MacKay.
Thank you. Thanks very much. Yes, as Stephen said, I've just come back from doing 5 years as a senior civil servant. I was the chief scientific advisor to the Department of Energy and Climate Change, where I was one of the people with oversight of climate science and geoengineering and many other policy issues. Let me tell you where I'm intending to go in the next 20 minutes. I want to take a critical look, a critical back of envelope look at climate change action scenarios, such as the ones that the IPCC published in the fifth assessment report. I want to help ensure that the scale and difficulty of those scenarios is being communicated well. That difficulty of climate change action then provides an argument supporting the Royal Society's recommendations of 2009 for research into geoengineering, both carbon dioxide removal research and solar radiation management research. To put it another way, here's what this talk is going to do. You might remember when Ken Caldera gave his talk this morning, Ken showed us a fan chart of credible futures, and he said in all of those futures that you may end up with states wanting to take action doing solar radiation management. And that fan chart of credible futures that Ken chose to show us was from the fourth assessment report, not from the fifth assessment report. And as a 5-second aside, Ken mentioned why he didn't use the fifth assessment report fan chart. And my talk is going to go and look at the scenarios that Ken chose to leave out, because I think Ken's judgment was that those scenarios are actually so challenging to implement. They might be technically feasible, but it's stretching credibility to include them as possibilities in our thinking. So I'm going to go and look at that, because I think if that's what Ken believes, I agree with him too, and that, obviously that's important as part of our narrative for why we're here. Okay, so that's where I'm going, and I'll use back-of-envelope calculations, which I love. And if you've heard me talk before, you may have heard this one. I just want to give you an example of a back-of-envelope calculation, which says, well, let's take the European policy that biofuels are magnificent, and we should have more and more biofuels for transport. There's a target of 8% or 10% or something like that for all transport, 8% of transport fuels to come from biofuels in Europe by some date. And presumably they're imagining increasing that fraction forever. So here's a calculation we can do. We can just say, well, imagine if you powered all the vehicles on a road from biofuels, and imagine if you grew those biofuels on the verge of the road, on a strip of grass alongside the edge of the road. How wide would the verge of the road need to be? Okay, so we can make a back-of-envelope calculation, just write down some numbers and get an answer. So we make up numbers like, we say, let's have one lane of cars. Let's say they're going at 60 miles per hour. Let's say they do 30 miles per gallon. That's per UK gallon. That's the average fuel efficiency of new cars in Europe at the moment. Let's imagine your biofuel productivity is, well, you have to look that up on Wikipedia, 1,200 litres of biofuel per hectare per year. That's the productivity of oilseed rape, which is the leading biofuel in Europe at the moment. And then you need a spacing between the cars. Let's say they're 80 metres apart. And now we've got enough numbers to get an answer. We don't need to know how long the road is, because the longer the road, the longer the biofuel plantation is going to be. Okay, what do? We take the first number and we divide it by the other three, and we take care with units, and you get a length. And the length is the width of the biofuel plantation, and the answer is 8 kilometers wide. And I love this sort of calculation because it makes you say, okay, maybe that European policy isn't quite a complete, perfect transport policy. Maybe just switching to biofuels isn't going to be a hunky-dory way of getting ourselves off oil. And I wrote a book full of back-of-envelope calculations like that one, which is available free online. And that book was aimed at trying to help people have grown-up conversations about energy arithmetic and energy options. It's been translated by volunteers into lots of other languages, and while I worked at DEC, it was also translated into spreadsheet. So the UK government has published several times a tool called the 2050 calculator for the UK, which is a completely open energy and emissions model of the UK, including costs and air quality impacts, and it's intended to be very clear what you're doing when you move the levers up and down. It's got levers for lifestyle change, it's got levers for technology choices, it's got levers on the supply side, and the user can choose any mix and then see, have you got a plan that adds up or not? So I'm delighted to have been involved in making that tool, and it's been imitated by another 20 countries now, so there are now 2050 calculators that are equally open for China, for India, for Korea, for Japan. There's a long list of other countries that have got similar open source energy models. And very recently, the team in DEC that made the 2050 calculator for the UK also led a project to make the global calculator, which is another open source energy and emissions calculator for the whole world. And the good thing about doing the calculator for the whole world is you don't just get, does the energy add up and what are the emissions? You also can represent climate consequences and see how your choices about wind and lifestyle and diet and so forth actually cause impact in terms of climate change over future decades and centuries. So I encourage you to use that tool. It's probably useful to many of you, and engage with it, and please help make it better. Now, I said that climate change action is difficult. In my book, I discussed how to make plans for the UK that reduced fossil fuel use for the UK to near zero. And I didn't recommend this particular plan, but this is an illustrative plan with lots of technologies in it to show the scale of what might be required. So this was a plan where there was a switch to electrification of heating and transport technologies, some efficiency savings, not enormous lifestyle change. Again, I'm saying I don't recommend this plan. I think lifestyle change might be helpful. And it gets its electrical energy and non-electrical energy from a range of sources visualized on the map here. The nuclear power was a 4-fold increase in nuclear over today's levels in the UK. The wind power would be 64 gigawatts of wind, which is a 6-fold increase in wind over today's levels, and twice as much wind as Germany has got. And you can see the wood and biofuel plantations visualized in green and yellow, contributing only this very small amount of energy on the right-hand side. So the aim of this book was to help people understand the scale of action required and how difficult climate change action is. You can make similar maps for other countries. When you do it for a country like the USA, which has a lower population density, you don't get quite such a striking intrusion of the low carbon stuff into the landscape, but nevertheless per person, the amount of stuff you need to build and the land area required for bioenergy or whatever is still just the same as it would be in the UK. So here's a visualization of 4 different ways of getting yourself 42 kilowatt hours per day per person of energy for the USA, with wind farms. Each of these 10 squares is the size of New Jersey. New Jersey is Wales, if you are British. 49 green New Jerseys showing the land area required to get you 42 kilowatt hours per day per person of bioenergy. And so the total of all those 42s is 442s, which is not as big as today's primary energy consumption in the USA. This picture on the left shows the recent 2008 primary energy consumption of the USA, which you can see is 250 kilowatt hours per day per person. So again, I'm not recommending this mix here. But this is just illustrating some options and the scale of them. And if you want to personalize it, here's a way of personalizing these 4 options. If you were getting 42 kilowatt hours per day per person of energy on average from wind in the USA, that would mean 1 2-megawatt turbine shared between every 300 people, which is, I think, doable, but it's a long way from where we are today. If you wanted 42 kilowatt hours per day per person from nuclear in the USA, it's roughly 1 nuclear power station per million people, so 7 nukes for Los Angeles, nukes for Chicago, and so forth. If you wanted 42 kilowatt hours per day per person of bioenergy, then that's 4,000 square meters, roughly, of bioenergy plantation. And if you want to do it with solar in deserts, then you'd need 30 of these mirrors per person and one of these towers for every 400 people. So that's a personalized view of the scale of some decarbonisation options for the USA. Let me now talk a little bit about climate science. I'm probably preaching to the choir here. You probably all know this, but just to check. I think this is the most important figure from the fifth assessment report from the IPCC. It shows how the size of climate change, summarized by a single number, of course climate change is high dimensional and complicated, but here's a summary number, namely global warming, the change in average surface temperature. It's a graph showing how climate change depends on cumulative emissions, and this is the most important message in my view. This little inset graph is showing the emissions rate, which could continue to rise under a business as usual, possibly a bit worse than business as usual trajectory in red, or humanity could do a U-turn and the emissions rate could drop to zero, as shown by the blue line. That's a technical possibility. And it's only if the emissions rate drops not to 50% of today, but to zero, that you stop cumulative emissions from growing. And because climate change is roughly proportional to cumulative emissions, it's only if you reduce emissions to zero that you stop climate change getting worse. So that's a very important message. It's a real inconvenient truth. It would be wonderful if all we needed was a 50% reduction, but it really is going to be a challenge. If you think of it in country terms and you say, which country can we look to as a model of what to do? Well, the answer is none of them, because all countries have positive emissions on the vertical axis, energy uses on the horizontal axis. As interim targets, you could say, well, let's have everyone emit 2 tons per year per person, please, or less. That means, could all countries politely get inside the red box? And then a few decades later, let's have everyone emitting 1 ton per year per person, which is shown by the orange box, which is currently occupied by the Democratic Republic of Congo and Bangladesh. So there's no role model you can look to to take this sort of action. It is difficult. Another thing I wanted to say about climate science is, looking back at this chart here, some people say, oh, well, who cares? The red line's okay. It's only 3 degrees of warming, 3 degrees of global warming, who cares? That's the difference between sort of morning and afternoon in Cambridge. It's not a big deal. So it's important to be clear what 3 degrees of global warming means, what it's like, and compare it to other changes of 3 degrees. So here's a change of 3 degrees globally. You can look back 20,000 years, and 20,000 years ago, the global temperature was 3 degrees lower than today. And that's because we were in the middle of the last ice age. Global sea level was 100 meters lower than today, and there was a mile or more of ice sitting on top of North America and Europe. So if you're ever in an argument with someone who says, oh, 2 degrees, 3 degrees, not a big deal, maybe show them this photograph of 20,000 years ago, which shows what the Earth looked like, and advise them that maybe a 3 degrees warmer world will be as different from today as this photo is from today. We've seen pictures like this before. This is a business as usual RCP 8.5 scenario showing the global average temperature increase, but segregated by region, showing the polar warming and so forth. And my feeling is this doesn't really communicate in a visceral way to people that this is something we want to avoid. So I'm always interested in finding other ways to communicate how different things the world might be. Ken showed us results from a science paper discussing the probability that summers in 2080 will be hotter than the hottest summer ever. I'd like to pull it back into our lifetimes. Many of us here will still be around in 2050. So what about in 2050? And let's make it more regionally specific for those of us who are from Europe. You may remember the summer of 2003, which is the hottest summer ever recorded in Europe. And then we can ask the question, by 2050, what's the probability that summer will be hotter than that hottest summer ever? Now, obviously, the answer depends on which computer model you use, and the computer models have different sensitivities. When I showed you that important graph with its linear slope, there was a pink sausage of uncertain sensitivity. And these answers are now from the Met Office model, which is one of the slightly more sensitive models in that pink sausage. And here are the projections for two possible future scenarios. First, I'll show you the dark blue, which is the U-turn, where we do what might be almost impossible and reduce emission rates to 0 by the end of the century. In that scenario, the black line is the history of temperatures in the summer, in June, July, August, in this region in Europe. And this is the record-breaking hottest summer ever. And you look forward to 2050, and if we get ourselves on that dark blue line, then this model is projecting that roughly 50% of summers will be hotter than that hottest summer ever. In contrast, if we stay on the red trajectory, which we're doing a reasonably good job of at the moment, then this is what it looks like. So I've put the mouse at the same height as that record-breaking summer, and you can see not only will almost all summers in 2050 be hotter than the hottest summer ever, but they'll be hotter than it by a really significant amount, most of them. So maybe this is a way of communicating a bit more viscerally to people to care about climate change. Okay, so climate change matters, cumulative emissions matter, that's bad news. And now let's look at the fifth assessment report, one of whose messages is, yes, we can take climate change action, the low carbon train is leaving the station, we all need to get aboard, come on guys. And I worry that maybe when the fifth assessment report and its summary were being published, perhaps there was a bit of over-optimism, a bit of wishful thinking, and a failure to communicate how extremely difficult it is to get on that low carbon train. So let's look at just a couple of details of the scenarios in the fifth assessment report. So what sort of things did the synthesis report say? Well, it said, there are multiple mitigation pathways that are likely to limit warming to below 2 degrees. So it's not just possible, there's lots of ways to do it. However, implementing such reductions poses substantial technological, economic, social, and institutional challenges. Okay, so it's a little bit difficult. Well, let's drill into that. What I want to do now is just look at the bioenergy assumptions in those scenarios and the carbon burial assumptions, just to get a feel for how difficult these things are. And I found it quite hard reading the fifth assessment report to actually find the numbers and to find them communicated clearly. Typically, you just have some graphs and there isn't any emphasis to try and help people understand the sort of gravity and enormity of these scenarios. So here's a graph, figure 6.20, which shows how much bioenergy, and it also shows how much of the bioenergy will be going into carbon capture and storage in these scenarios. And the scenarios here are shown in gray, which is a baseline business as usual scenario, in orange, which is a sort of half-baked climate change action, probably wouldn't get you to the 2 degree limit. And the blue scenarios are the ones that have a chance, a 50-50 chance or so of staying below 2 degrees. So what do we see here? Well, I've highlighted in red and green for the blue scenarios and orange respectively, what's being assumed about the amount of so-called modern bioenergy that you have in the year 2100. So if you want a scenario that gets you to 450 ppm, you need, what does this say? About 275 exajoules per year. Okay, let's back of envelope that number and understand what it means. Or if you want the half-baked climate change action scenario, then you need 200 exajoules per year. And in these 2 points I've chosen here also happen to show 75% of all that bioenergy going into carbon capture and storage, or 60% respectively. Okay, so whether you go for genuine, complete climate change action and you sort of solve the problem, or you go for the half-baked one, there's very large amounts of bioenergy being used here and lots of it going into CCS. How much? Well, what does 275 exajoules per year mean? Allow me to do some back of envelope calculations. First, let's express it per person. That is 23 kilowatt hours per day per person, equally shared between 9 billion people. 23 kilowatt hours per day per person, let's compare that with the map I showed you earlier. This map showed the area required in the UK to get 5 kilowatt hours per day per person from wood and 2 kilowatt hours per day per person from biofuels. That's a total of 7, and here we're talking 23. Okay, so that's a lot of bioenergy. Or if you want to visualize it in terms of areas, I'm going to assume half a watt per square meter as a typical productivity, and people could feel free to argue with that, but if we make that assumption, which is my favorite sort of central number for good bioenergy, you need 17 million square kilometers, which is 2 USAs, 2 continental USAs, roughly 10% of the world's land surface area to deliver that much wood, or whatever the biomass is. The authors of the scenarios that got into AR5 would disagree with my assertion that bioenergy productivity might be half a watt per square meter. They say, oh no, it's going to get far, far better. Well, that's something that needs to be communicated. They need to communicate clearly. They're assuming a radical improvement in the efficiency of productivity of modern bioenergy. And even then, even if you do make it more efficient, you still will need to be shifting 17 billion tons per year of bioenergy. And I'll compare that with the oil industry in a moment. We'll see that's about 4 times the size of today's oil industry is what's being assumed here. So here's a rhetorical question. Is there any possible inconsistency with this view of the potential important role of bioenergy with other things that the 5th assessment report said, in particular Working Group 2, which looked at the impacts of climate change? So Working Group 2 said, we're expecting climate change to cause all sorts of problems in rural areas. There's going to be food issues and so forth. So my feeling is that there is a potential inconsistency between using lots of the world for bioenergy, especially the developing world is where most of this modern bioenergy is going to magically be sourced, and that's the very area which is going to be disproportionately affected by climate change. Here's another criticism of the AR5 scenarios. They did sensitivity tests to their scenarios, and they said, let's rerun our models, assuming that you can't have something. So let's say no nuclear, let's say no carbon capture and storage, let's say limited bioenergy. Now, when they said limited bioenergy, what did that mean? Well, here's what they meant by limited bioenergy. They said, we're going to allow a maximum of 100 exajoules per year of modern bioenergy, and we'll call that limited bioenergy. Now, compared with today, that is a 5.6-fold increase in modern bioenergy over today's levels. So, imagine if they'd done the same with nuclear, and they said, yeah, we're going to have a limited nuclear scenario in which nuclear is only 6 times as big as today. Everyone would have screamed blue murder, and they would have said, that's not a reasonable scenario. Yet, for bioenergy, they've gone ahead and assumed that modern bioenergy can increase 6-fold. So it bothers me that they haven't really done a stress test, a sensitivity test to what if you really couldn't do sustainable bioenergy in the way they're assuming. Okay, thanks. So in summary, how much bioenergy are they assuming? Well, even their limited bioenergy scenarios are assuming what I would call a massive use of modern bioenergy. Moreover, I'm sure their models are assuming that carbon is being magically accounted for correctly in all of these calculations. So they're assuming a global carbon price, and they're assuming that farmers and forestry managers will all respond to that carbon price in a way that shows that they're aware of the carbon in the landscape. And that itself is a very big assumption to make. And when I was at DEC, I was one of the authors on a report called Life Cycle Impacts of Biomass Electricity in 2020, which looked at the possible carbon footprint of our current practice of cutting down trees in North America, shipping them through the Panama Canal and across the Atlantic so that we can set fire to them here in order to deliver so-called renewable energy to Europe to comply with the Renewable Energy Directive. And what our work showed is that current sustainability criteria don't actually ensure that this is low carbon at all. It is possible that it's low carbon, but it's also very possible that you are deforesting the landscape in average terms, so you're actually causing a carbon release from the landscape. The second thing I want to scrutinize is how much carbon burial do these scenarios assume, the scenarios that achieve successful climate change action. So again, it's quite difficult to find the numbers. Many of the graphs in the 5th assessment report just show net emissions, and they show net emissions, emissions rates dropping to 0 in these blue scenarios here. And here's another scenario that allows itself to overshoot, and then net emissions drop to 0, and then net emissions become negative. If you're only showing net emissions, you're not communicating to people the size of the CO2 burial that you're assuming. Because if you've managed to get emissions rates to 0 at some time, surely there are still some people burning fossil fuels in that scenario, which is positive emissions, and so to have net 0 emissions, there must be equally large negative emissions going on. So I find these graphs quite dissatisfying because they don't segregate out the negative emissions from the positive. We can zoom in and get a hint of how big these negative emissions must be. This is an energy-only net emissions graph, and you can see that the energy sector net emissions are negative. And if that energy sector is still burning fossil fuels, which I think is credible, then obviously you have to have negative emissions at a scale bigger than this black thing, which is minus, what's that, minus sort of 4 billion tons per year of CO2. If you drill into the fifth assessment report, you can find some numbers. And here's an indication of the scale of carbon burial that's being assumed in these scenarios. It's on the lines of, in 2100, by the end of the century, it's somewhere in the ballpark of 10 to 20 or maybe even 40 billion tons per year of CO2 being buried. So now let me picture this for you and compare it again with the oil industry. Here is a radical climate change action scenario that gets the emissions rate down to 0 by the end of the century and might limit global warming to 2 degrees plus or minus quite a lot. Being realistic, that's not going to happen, but you might still hope that we do the U-turn a little bit later, and then to keep within the budget of cumulative emissions, we switch on net negative emissions to compensate for this overshooting here. You have net negative emissions for the final decades. This is when the aliens arrive in 2050 with their magic vacuum cleaner to allow us to do the negative emissions. So making explicit what might be going on, in red I'm showing what the positive emissions would continue to be. This is, I'm just imagining that we managed to halve our use of fossil fuels compared with today. That actually means that the negative emissions rate that's required is the difference between this red line and this purple line, which is ballpark 20 billion tons of CO2 per year. As I said a moment ago, the scenarios we're assuming. Okay, now let's compare that with something. World oil production today is 4.2 billion tons per year. So these successful climate change action scenarios, which I agree are technically deliverable, are assuming that by the end of the century, we're creating a carbon burial industry that's 4 or 5 times as big as today's oil extraction industry. And that would be a completely government-motivated industry. It wouldn't have any direct profit motive. It would only happen because of there being a carbon price. Whereas in contrast, the oil industry today has grown up to the size that it's got because of the profit motive and enterprise and so forth. So I do think it's stretching credibility to imagine that we are going to manage to create that enormous industry by the end of the century. I think policymakers should be trying to enable that industry to be created. There should be clarity about carbon prices and so forth, so that there is an incentive to try and create a negative emissions sector. So to wrap up, what I've said may be a little bit depressing. I could tell you all sorts of optimistic things as well about the prospects for reducing the costs of low carbon technologies, but why we're here is to talk about geoengineering. And I hope what I've said about the difficulty of climate change action does provide a motivation for saying, yes, humanity may be interested in having some other options as well as just plain emissions reduction. And I want to close by showing you a figure that John Shepherd, who was the chair of this report from the Royal Society, and who was also the chair of my science advisory group when I was chief scientific advisor at DEC. This is a sketch that he showed me to just help people think about all the options that society has. Here's business as usual. The axes are not labeled, but the vertical axis is some measure of climate impact. It's something along the lines of global warming, and time is unlabeled on the horizontal axis. Here's business as usual. Society is going to do emissions reduction and reforestation to some degree. This is one of the levers we can use. And it's quite likely that if we only did that, we'd end up with very uncomfortable climate impacts. Society could also do carbon dioxide removal at very large scale, but that will be slow to implement. And if you finally get it going and start actually sucking CO2 out of the air in net terms, then you can undo the level of global warming. And in that interim period, society might be interested in solar radiation management. Still, we may be in an uncomfortable world. We'll cope with that by adapting. I'm showing adaptation as a sort of quasi-reduction in effective temperature, if you like. And then what's left in this diagram is suffering. So these are society's options. Thank you very much for listening.
Let's have just 2 quick questions here.
Sorry to keep interjecting. I'm an engineer, and I'm obviously aware of all the problems with the pollution and CO2 emissions. And I decided to take it upon myself to turn my home into an off-grid home with 680 watt panels and batteries and a 250 watt turbine. And I've actually helped people do 10 homes convert. So if one little engineer can actually do that, can't we all do something similar? I decided that I wasn't going to wait for government initiatives. The prices of panels was dropping rapidly because of, obviously there's a huge interest around the world with PV panels. So I decided to do it myself. And once again, somebody saw it and said, could you do that for me? Yep, I can do that.
Good. So the question is, can we all...
How would you feel?
Can we all do it individually? So let me respond with a sort of yes, but. So in our 2050 calculator, yes, you can crank up small scale wind. So that's one of the levers you can crank up. And this has been developed in collaboration with many stakeholders, including Friends of the Earth. So it's all got a lot of stakeholder buy-in. And this particular lever, small scale wind, doesn't have a massive impact. The reason it may have had a massive impact for you is I suspect you live in a low population density area. So you can have a reasonably large wind turbine, but
When the sun's not shining.
Okay, oh, you've got a
when the sun's not shining and the wind is blowing, and so this
Okay.
250 watt is a tiny, tiny thing.
Okay, all right, it's a tiny wind turbine. Okay, I'm sorry, but I don't think that that's going to be a solution for most people because most people don't have enough wind. Solar panels, they work in the summer. They're expensive, the costs are coming down. They work in the summer, they don't really work in the winter. And so if you want security, you have to have extremely large batteries to get you through, or you need a connection to a decent sized wind turbine. And your home is not your whole footprint. Your home is probably only about 10% of your true energy footprint, because you also have transport, you have stuff that you buy. You depend on industry.
Yeah, I can run a heavy load during the day when the sun is shining, so I can attach my car.
Listen to me.
Yeah,
listen to me. Your home is only a tiny fraction of your footprint. This is a delusion that a minister who I won't name had when he joined the Department of Energy and Climate Change. He gave a speech, he said, look at this wonderful wind farm we're about to build. It can power 5% of the homes in the country, so we only need 20 of these and we're done. He thought homes was the country. The home is only a tiny fraction of the energy consumption of the country. If you want to power a country, you need to power industry, transport, heating, all these other things, the provision of stuff for you. So yes, you can do some stuff to power your own home, but it's actually a delusion that cities could power themselves. Cities will have to depend on the countryside. You have to do big stuff.
Yes, we have big stuff in Greece.
And it sounds like your solar panels were big stuff. You need many square meters of
I have
solar
six
panels.
180 watt
Yeah.
panels.
And
I create 8 units a day, which having insulated my home.
8 kilowatt hours per day.
Yeah.
Good. And the average British person today is using 125 kilowatt hours per day.
I'm
if you
aware
look at the entire
how much I
footprint.
use.
I think
So
we have to go on to one more question up the back there.
I think just for going from the engineering part here, you and a lot of people talk about carbon capture and storage. Do you actually believe it's realistic?
Is carbon capture and storage realistic? Absolutely. It's not been done at scale in the UK, but every component of the chain has been done at scale. There are real power stations in the USA and Canada that are capturing CO2 at scale and burying it in the ground. They're doing it because that CO2 has a value for enhanced oil recovery. So it's absolutely doable. Yes, we'll need some more R&D to verify that the places we could put it in the North Sea are going to be satisfactory stores, and you need a carbon price signal to get it to happen. But I think it's probably going to be one of the most cost-effective ways of taking climate change action once we have a sensible carbon price across the whole economy.
Okay, David, I think we all appreciate considerably the green and pink columns that appear in the right-hand side margin of your book. And I certainly would like to thank you for such a clear exposition of the accounting for the energy sources and sinks. But when you come to think about translating all of those options into reality globally, we begin to think of a massive computer program which optimizes all of these factors and all of the proportioning in those columns in such a way that it commands the price and hence extinguishes the idea of the free market as a control system, Adam Smith's idea of the invisible hand, and replaces it with a sort of massive global brain which controls the energy sources and sinks. Your thoughts?
Okay, I think what you're describing is a possible policy approach to, and I think there are many policy approaches. So the global calculator is not an optimizing model. It's a big model of the energy system that allows you to envisage anything that's technically deliverable, and it doesn't impose a particular policy approach or an economic optimization approach. So I think that's a helpful starting point for helping people understand options. I agree with you that if we had an economy-wide carbon price, and if, as David Keith has said, if people who bury CO2 are able to bid into that and get credit for burying CO2, then you could have a nice self-stabilizing system where the price of carbon emissions will be the price of burying CO2, and that would be a very nice endpoint to get to. But I don't think that's the only policy that we need, because there'll be all sorts of sectors that wouldn't respond to that carbon price. So I think society will need regulation as well as an economy-wide carbon price.
I think we'll have to have the questions more questions in the coffee session. I'd like to thank you again. And now we've got Lynn Russell from the Scripps Institute, who's going to be talking about the ecosystem effects of SRM. She took me along the pier at Scripps. It's a lovely walk, well worth doing if you ever get a chance to do that. And I think she's done some work on smoke flares to simulate marine cloud brightening. So, Lynn.
So thanks to the organizers for inviting me and for giving me the task of talking about ecosystem impacts. And I'll come back to at the end how I got into being interested in this. But I will put out the disclaimer at the start that I am not, my work focuses on aerosols and clouds, and I'm not an expert in ecosystem impacts, but I'm going to tell you why it's important to this issue of solar reflection methods, and I will let you know about what we know so far from the literature on ecosystem impacts. I don't have to define this in this audience, as we've heard it several times today, but the question that I'm asking is how these two approaches might be affecting ecosystems. And so first, I'll provide motivation in saying that why is research on ecosystem impacts important for simulating SRM? And that's based on the fact that climate models indicate that at least 2 SRM methods are technologically feasible for reducing warming as your target, comparatively cheap, and climate models don't have cost, but they do calculate the burden required. So based on that, you can estimate cost, and reasonably fast relative to CDR. But many ecosystem processes are not included, at least not in sufficient mechanistic detail, in climate models in order to fully simulate prognostically or a priori what will happen as the Earth system changes. And so models can't simulate processes they don't include. I'm sure that's straightforward. So by not including all of these relationships, we are necessarily missing some of the impacts. And so what can we do to get these processes into climate models? Controlled experiments would help a lot in terms of understanding the processes. You'd still have a scale-up problem, but there's been few controlled experiments, and there's few mechanistic ecosystem models that have been run for SRM conditions. So what do I mean by ecosystem impacts? And if you look in the ecosystem literature, there's kind of two categories of ways to think about this. And these are what Georgina Mace proposed in her report a few years ago. You can think both about the ecosystem components, which would include community structure as well as taxonomic diversity. A second category then would just be biomass and productivity, sort of how much living things are out there. And then you can also think about the biogeochemical cycling, so how nutrients and other components as chemicals, we often think about nitrogen as well as carbon, are cycled through the atmosphere and where the reservoirs are and what the fluxes are through each of those components. The other way to think about this is in terms of thinking about ecosystem services, and those are generally divided into the following four categories. The first being supporting, so including primary productivity, since that leads to food supply, as well as other climate impacts. Provisioning, which is directly the fuel and food. Regulating in terms of the role that vegetation and other things play in water quality and other components of the Earth system. And then finally, cultural, which the obvious example is the aesthetic impact of ecosystems, but I'm going to suggest a slightly different cultural one too. But the question then is that there are many, what has been done in terms of ecosystem research is there are models and measurements and analyses that have projected impacts of greenhouse gas, GHG, warming on both of these types of categories. And so the key question is whether SRM would make these changes better or worse, changes to ecosystems. So again, we're not necessarily thinking about the absolute change, but mostly what we're thinking about as is true for temperature is how much better or worse than the SRS2 or any particular scenario you want to focus on. And I'm going to, just as an example of the question of ecosystem services, I'm going to point out this cultural one because it's maybe the one that we don't have explicit metrics for and probably won't, but it's nonetheless very important. And one example or way to think about these other than just, oh, it's a pretty mountain, is thinking about how we perceive the ecosystem that we're in. And this is Carolina Sebeka, who's here, her idea of thinking about the ecosystem in which we reside and thinking like a cloud as following on to the Aldo Leopold sort of approach of thinking like a mountain. And what is really interesting about what she's done is she's, well, first designed a cloud liquid water sampler, which I think is just fabulous, by all DIY components. And so she's gone out and sampled cloud liquid water. And then in terms of thinking about how the ecosystem is affecting us, she's asked people to document when they drink this cloud water, how they then change their perception of their relationship to the environment. So there's lots of different cultural aspects that you can think about in terms of ecosystems, again, that are difficult to quantify, but probably very important for our current human culture. I'm going to focus on sort of the non-human health aspects of ecosystems. Arguably, that's a well-limited approach, but what we're focusing on here is those that would not be, those impacts that would not be taken into account by a human-centered or just focusing on human health aspect. And the way I initially got involved in this is as a member of the International Geosphere Biosphere Program Board. I pointed out that as geoengineering proposals were starting to come together, that no one really had taken the approach of, or taking the time to look at the possible ecosystem impacts of these proposals. And by pointing out that omission, I somehow became volunteered to do it. And so the result was this report, which I was fortunate to have a number of ecosystem experts help and contribute to, several in this room today, for which I'm very thankful. And essentially what we were able to document is that research has shown important greenhouse gas warming effects on primary productivity on land and in oceans, and I've just put a couple examples of citations up here. The possible effects on vulnerable populations and species, and also studies on the adaptation rates of species that also have implications for the rate of warming or the potential offset by cooling and potentially from termination effects. And as you can see, this was designed not as a comprehensive review, but more as laying out a plan for what we wanted to happen, and it had 4 components. It was to design experiments that examine the ecological consequences of an engineered planet, i.e. a cooler one than a globally warmed one, but still high carbon dioxide, and to define the baseline observations necessary for interpreting results of SRM experiments, and there it was mostly envisioned as modeling experiments. Third, to define the types of models necessary to address ecological impacts of SRM. And this is where there is still uncertainty, and there was hope that ecologists could define the key processes, scales, state variables, and sensitivities to rates of change for modeling ecological impacts. And then fourth, to define the models and analyses necessary for comparing geoengineered and non-geoengineered worlds. And so what I will show to you today is what the research I found that has been done since then. In other words, how much everyone listened to our brilliant recommendations. And you'll, that's next. And so I'll divide this talk into 3 categories. The first 2 are shown here. I'm just going to review briefly, because we've heard a lot already today about the meteorological or climate impacts that will have effects on ecosystem viability and productivity, but don't actually necessarily do all the modeling that you need to really understand population changes. And so the first of these is temperature and precipitation changes relative to a warmer world. The second is the longer term and feedback effects, including QBO mentioned this morning, and productivity changes. So the models that actually do include net primary productivity, or theoretically also on populations. And then secondly, the chemical impacts, which would affect biogeochemical cycling and potentially toxicity, as well as ozone depletion, and then explicitly the consideration of what happens to all the aerosols we emit, where do they deposit, and what is the effect on ecosystems they deposit on. So these studies aren't actually sort of what I said the research needs are, but this is what's been done, and they do provide input to ecosystem models, but most of them don't include a lot of detailed ecosystem processes. And so what about other impacts, and particular effects on populations, phytoplankton emission changes, changes to fishery production, the list could go on, as well as other unintended and unforeseen consequences. So I'll get to that at the end, and there is one really interesting study from sort of close to here, down in Plymouth. A group has done an ecosystem model. I think it's close relative to San Diego. And so I'll get to that at the end. So first, just as a review, there have been a number of studies who have looked at precipitation impacts, both for idealized SRM, stratospheric aerosols in particular, and then marine clouds. So here by idealized SRM, I'm referring to some of the shading experiments where there wasn't a particular, where the key is reduction in the incoming solar as opposed to a particular aerosol effect at a particular altitude. And so there's been studies showing global precipitation effects as well as uncertainty on precipitation. There's been regionally focused effects that were noticed in terms of reduced tropical precipitation. Enhanced Sahelian drought is another possible effect of the stratospheric aerosols. A number of studies on marine clouds, including reduced precipitation in South America, as well as effects on aridity and tropical precipitation. Some additional long-term effects, a new study was presented this morning by Scott Osprey, or at least it was new to me, also on the QBO, the quasi-biennial oscillation, and their results look to have some similarities with this previous study in terms of affecting the frequency of the different QBO phases, but it seems like some of the results are also different, so different models giving us different impacts, and so that's for multi-year cycles. Another multi-year cycle that's been studied is the El Nino Southern Oscillation, as well as the West African monsoon, and how mesoscale convective systems are affected, and so just a variety of results there. And so, but the first study I want to talk about that's actually translated those precipitation and temperature effects into productivity is from the GeoMIP comparisons. And this is just one part of that result is shown here. And the top graph is the difference between the SRM and just greenhouse gas warming. And then the bottom graph is the net primary productivity for just SRM. So what you can see by the lack of colors in the top graph is that it's pretty similar to the greenhouse gas warming run, with a few differences being this slight increase here relative to greenhouse gas warming and slight decreases here. And so that's the, but this is what it overall looks like relative for just the productivity increase. And this was the all model ensemble annual average for all the models that predicted net primary productivity in this intercomparison. And the, right, and so if you look at those model predictions as they trend by year on an annual mean average, you actually see that there's quite a bit of spread between the rate at which the net primary productivity increases for the different models. So several factors difference between the highest and the lowest. And what is actually interesting is that there's different rates of acceleration of the productivity for the different models, and that rate of acceleration is very dependent on how nitrogen is included in the nutrient fertilization effect in the land vegetation models, as well as a couple other interactions. But the main thing that all the models do agree on is that as we'll have higher CO2, but not excessively warm, that you will see the same kind of increase in net primary productivity that you expect in greenhouse warming. And so in addition, so this was the Kravitz et al. Study as well as the Jones et al. Study in 2013, both on the GeoMIP multi-model intercomparison. There's a couple other studies that I won't talk about today that looks at more particularly, rather than the idealized SRM, the marine cloud effects on continental drying and some regional canceling of some of those primary productivity effects. And so back to what about ecosystem models and effects on populations. So the most detailed mechanistic ecosystem model results that I found are those showing reduced productivity in subtropical gyres in a 1D column model run over the South Atlantic Gyre. And so this is a very oligotrophic or relatively low productivity region, but is important because even though it's low productivity, it's it was a straightforward system to model, and it's representative of a large fraction of the ocean. And so that's why they chose to focus on this. And what you can see, and this gives you an idea of what the complexity of including ecosystem impacts is that it actually, the effects of SRM are different for different populations and species. And so in their model, they classify phytoplankton and other plankton into 4 categories, and they look at both total chlorophyll as well as phytoplankton biomass, and then they look particularly at the large phytoplankton biomass, which is where they saw some of the important changes, and they actually saw a shift in the size distribution of the phytoplankton associated with this SRM and actually CDR scenario. So I'll show you that next. On the whole, though, they actually found that while the distribution changed with both depth and size of phytoplankton, that the gross primary productivity minus the respiration, which is what the quantity they're modeling, stayed about the same. And the complication in this study is that I think they wanted to kill 2 birds with 1 stone, so they not only did SRM, they also did CDR. And so they've got a nutrient addition to the phytoplankton, and then they have a shading period in their model, and it's a very simple shading algorithm. And then they essentially constrain to sea surface temperature. And they look at the effects of that. And as you can see in this graph, there's it levels out. So there are other potential impacts. There is discussion of biodiversity reduction associated with SRM. I'm not familiar with the details of that study because it was in Chinese. So if anyone wants to volunteer to help with that, let me know. John Latham, who can be here today, has also looked at coral bleaching and essentially how just mitigating the sea surface temperature changes will reduce that coral bleaching with marine clouds. And then there's also been discussion of potential for toxic plumes. And so I'm going to come back to sort of how I got into this in the following way, to mention that there are also chemical impacts that have been looked at in terms of stratospheric ozone depletion. There's a couple studies, and so that affects ecosystems by ozone absorbing UV and allowing organisms to not be damaged by that UVB radiation. And there's some evidence based on models that stratospheric aerosols might interfere with the ozone layer recovery. In addition, there's a couple studies, one study I should say that has looked at the contribution of proposed amounts of sulfate stratospheric aerosol to acid rain and shown that that's relatively small. And so my interest is sort of in looking at deposition of marine clouds, where while we carried out an experiment with paraffin that I'll tell you about next, and one of our questions was what was going to be the impact of this paraffin on the local marine region as well as coastal regions. Why did we do this? It wasn't a geoengineering experiment, but we had studied for a long time the ship emission effects on clouds. And while I wouldn't exactly call this a natural analog, it's an existing analog. What are those aerosols that are being deposited in marine regions? They're typically about half sulfate and half organics, including trace amounts of carcinogenic polycyclic aromatic hydrocarbons, which is in most fossil fuel vehicle emissions. And so rather than using that, which also costs a lot more, we used paraffin oil and a smoke generator that gives us a large source of particles without having to burn quite as much fossil fuel, in fact, much less. And this was based on sort of old technology, which we acquired on eBay for $100 each. We bought 4 of them and got 2 of them to work about half the time. And then what's used to make the smoke is paraffin oil, which the National Institute of Standards considers environmentally benign. I'm sure that's based on criteria that weren't exactly relevant to this study. But it is the same material used for skywriting, which is where airplanes will go up and intentionally write messages in the sky about what car you should buy or who you should marry or happy birthday or something like that. It's also been used for science since the 70s. This is a Brookhaven National Lab study, and the photo's really bad. It's a rescan black and white. But they used a smokestack with artificial smoke to watch where the plume would disperse as a function of the stratification of the boundary layer. So not exactly new, but if technology works here, I forgot to plug in the sound. But it's this really lovely sound that's somewhere between a dying motorcycle and somewhere. Oh, there it is. Yeah. Okay, you guys are gonna like this. Coming around to the right. And so we're running these smoke generators on this ship, which you might notice the ocean isn't exactly calm. It's going up and down at a fairly high rate. And then there's an aircraft that is gonna appear right about here and go through the plume and then sample the plume as it impacts the cloud up there. So that's the experiment and the measurement. And I'll just go ahead, if everyone's heard enough of this, it was 12 days with this noise, makes me not the best fan of it. But the idea was that we could then have the aircraft sampling those emissions as they interacted with the cloud and actually better understand both the microphysics and the chemistry of that interaction and hopefully feedbacks on the meteorology as well, using satellites to quantify changes in reflectance. And so the idea was a collaboration with 5 scientists. This was our E-Piece experiment, which so far has 20 papers published to date from these 5 groups. All of them focus on sort of outstanding scientific questions about aerosol cloud interactions, from chemistry to microphysics to meteorology, that are relevant to reducing climate change uncertainties. Here's one of my favorite results. We actually could measure the composition of both the droplets and the particles and show which particles were actually making the droplets. In the case of the smoke, we could actually show the smoke was making the droplets because this green part was the smoke, as opposed to in cargo ships, you have half organic and half sulfate, and that was what was making droplets in the case of cargo ships. And so comparing them to kind of the clean marine background was a big focus of this project. It was, not a project focused on SRM, but you can look at both the amount of CO2 produced in moving the 2 kinds of ships, a cargo ship, which go sort of every day and cost about $100,000 a day in fuel, mostly. There's 10 or so K in there for people to run it. And on days that they make clouds, if you assume a 100-year time horizon for the CO2, you get a cooling to warming ratio of 2, but high uncertainty, plus or minus 1. And the little ship with the smoke generator, because we're burning a much smaller amount of fuel, making less CO2, but still, when we make a cloud, we get a cooling to warming ratio of 50 to 1. Thank you. And so how did this relate to ecosystem impacts? Mostly because we would have liked to quantify them, but that wasn't part of our scope. We were focusing on the aerosol cloud interactions and how that actually works and the role of organic components relative to sulfate, especially in light of the new regulations on using sulfur fuel out to 200 miles from the US. But what might we have done to help to quantify ecosystem impacts better? Certainly small-scale measurements of phytoplankton in the column would have been a good way to constrain the type of model that Hardman Mountford used to look at changes in productivity and see if those calculations are reflective of the Eastern Pacific. You could try and do that behind a cargo ship. They move kind of fast, and so it's not as easy to track that as it is in a controlled emission experiment where we have the smoke generator and can take it where we'd like it to go. The other component of that would be actually running the ecosystem model, both on localized regions and downwind coastal regions. So I'll just mention one last aspect before I wrap up. One of the interesting components of the Earth system and ecosystems in the Earth system is that they are sometimes surprisingly resilient. And so this is kind of a good aspect of this. And so in this collaboration with Mark Stafford Smith, we actually looked at how doing regional SRM might have fewer impacts than trying to do something more widespread, suggesting also that populations have a better shot at adapting the slower the changes are, and so that would also help on that account. So I'm just putting this up again as kind of my main message here, and with that, thank you for your attention, and I'm happy to answer any questions.
Right, we have one question here. While the microphone's coming, I'd like to point out a little experiment happening on the front table here. The difference in albedo of the two jars is of scientific interest. So there's one down here. Yes, have you got, can you bring the microphone down here?
Lynn, it's been my impression that the work on ecosystem effects of global warming puts a lot of stress on temperature because of changing habitat ranges, more so than on changes in precipitation or other things. Isn't the main metric for looking at ecosystems effects of SRM to compare it to the effects of increased temperature in the global warming without SRM scenario, rather than looking at effects of SRM itself?
So certainly in GeoMIP that's true, because as they designed the experiment to reduce the temperature, you already kind of had that improved, right? That was the given. If you designed your experiment or designed your SRM to achieve something else, then you could think about the problem differently. But I agree, it is most of what my understanding is drives, well, there's two things affecting the net primary productivity. There's the temperature as well as the CO2 fertilization effect is kind of what's big there. So I think that's true.
Okay, at the back there, Andrew Lockley.
Yeah, I wanted to ask, have you looked at this the other way around and looked at the effects of either solar radiation management or on global warming on the global surface albedo? So for example, if you get dieback of the Amazon and it goes from dark green rainforest with white clouds over it to more intermediate grassland, which is paler but has less cloud cover, then that has a big sort of SRM type effect. It changes the global albedo. So have you looked at the impact the other way around, the kind of ecological response to climate manipulation or climate change, and then consequentially the internal feedbacks in the system that change the albedo and other factors?
No, I have not. Has that been done? I haven't noticed it in my reading, but someone else might know more here in the audience. But if I understand your question correctly, you're asking about the like the clearing of the rainforests in South America and that effect on albedo. So again, that could be another way to think of.
Well, no, sorry, just to clarify, I'm not asking about the clearing of rainforests. What I'm saying is that you're saying, well, what will be the effects of SRM on ecosystems, right? What I'm asking is the opposite effect. So what is the effect of natural changes to ecosystems as a result of climate change or SRM on global albedo. Yeah, so it's the opposite. It's to what extent ecosystem changes force the climate, rather than to what extent do climate forcings change ecosystems.
So there has been some work on that, but I haven't done it, and I don't have the details at hand. Because yes, people have looked at what we expect the changes to land albedo are, as well as other changes to albedo due to, well, whether you call them ecosystem changes or human-induced changes, is debatable as well.
Okay, over here.
Hermann Held, Klima Campus Hamburg. Thanks a lot for this great overview. Do you see any chance to compare the risks of the termination shock that could happen to the benefits of SRM at this point in time?
With respect to ecosystems, or? Yeah, I mean, the concern that we had in the report and the termination effect did sort of feature strongly in that concern, just because if you continue to emit CO2 at current rates while doing SRM, you would risk a very large termination effect, as was discussed earlier today. I would tend to, at this point, quote the NRC report that Ken mentioned, was released last month, where we very strongly said that there isn't really, that it would not be a good idea to continue to not mitigate CO2 and to do SRM, as the 2012 paper definitely said that if you have sudden termination by stopping SRM, which you make worse by continuing to emit CO2, that's more likely a bigger problem for more components of the ecosystem. And the reason is back to what I was mentioning about the resilience of ecosystems. Ecosystems can typically, or are better at surviving over slower changes that occur less suddenly. So yeah, so we do think sudden termination is probably worse than gradual warming.
Okay, by the way, the termination effect is maybe taking bad things in 10 years. If you switched off air traffic control, it's about 3 minutes. Does that mean we should never have had air traffic control? Was there another question over there? No? Right, well, let's close that down. Thank you very much. Can I... Yeah. We've lost a speaker from the next session, and we've started this one a bit late, so all the times are going to be pushed on by 15 minutes. But could I ask you to be back here promptly when the next session begins? It's really rather rude to the speakers if people are still trickling in. Thank you very much.
3:45 for restart. Thank you.
Okay.
Very good.
Thank you. Doing a good job, by the way.
But somebody's community is choosing, a big power to come in and economic sanctions.
Can I try it in? Yeah, it's working.
so you guys know, the speaker.
Okay, they got it.
Are they Ben Kravitz? You know about?
Yeah.
Okay, let's make start.
If I could ask people to take their seats and quieten down their conversations, please, that'd be lovely. Thank you. Okay, so we have our second technical session of today. In the programme, we have 4 speakers. Unfortunately, Andy Wiltshire is unwell and is unable to attend today, so we just have 3. And to keep it all very 2.0, Ben Kravitz will be joining us via Google Hangout. So, I ask for your patience when it comes to the questions component of that and the success rate of that in itself, because there will be a 30-second delay with Ben. So what we'll do for Ben, who's the second speaker, is we will take the questions at the end, pose them to him, all wait patiently for 30 seconds, which will sound like his answers come with a lot of gravitas, and then he will provide us with his esteemed wisdom. But first of all, we're going to start with Professor Piers Forster from the University of Leeds, who's a Professor of Climate Science there and was the Principal Investigator on the Integrated Assessment of Geoengineering Proposals research project that just finished in February to talk to us about precipitation and solar radiation management. So over to Piers.
Yes, okay, good afternoon everyone. What I'll be talking about isn't my own work, of course. It's work by Julia, who's sitting at the back there. Julia, do you want to give everyone a wave? Okay, and I do want you all to remember who Julia is. Because what I'm really talking about is by the conclusion of Jim, Phil, David, Keith, and Ben, who's about to talk, why I think their conclusions on precipitation are really incorrect. So, to create a bit of controversy. So, okay, what we did in our project that I think was very exciting and really for the first time was that we, within the same analysis framework, within exactly the same GCM, we looked at 6 different geoengineering technologies. And this does enable us to effectively compare these different technologies. So, what I first want to talk about is what we were comparing these technologies with. What we were comparing them with was the RCP 4.5 scenario. So what I put up on the screen is the RCP 4.5 scenario in 2049, 2059, and you see the surface temperature change and the precipitation change, and I also express the changes just as you saw in the plot by Ken Caldera today, is that listen on the number of standard deviations in the kind of change from today in the 20-year standard deviations, and you can see on this that in terms of that deviation, you see the bigger changes in the tropics because of the bigger internal variability in the Arctic and the Antarctic. And what I also want you to realize on this diagram is that perhaps these look like big changes in precipitation, but if you do look at the changes in precipitation in terms of the standard deviations, they are comparatively insignificant compared to the number of standard deviation change you see in the surface temperature. So they are generally within 2 standard deviations, and what you also see is there is whereas not in the two standard deviations, you do see a general reduction in precipitation. Okay, before I talk about precipitation, I'll just show you one plot to do with the surface temperature changes. And this just show with the technologies, we couldn't all get them to give the same surface temperature change each other. So this does show the evolution of their surface temperatures. And you can see, for example, with changing the crop albedo, you do not get a big change in surface temperature. It's almost impossible to achieve a big change, but you get ones that really do have a big change. And what I want to do with this diagram is to try and compare the changes in surface temperature to the changes in precipitation. So what you see on this diagram, you see the globally average precipitation, and that to first order really does look a little bit like those changes in surface temperature. So you do appear to have this reduction in the surface temperature, but the interesting thing about the precipitation time series is that if you look at them over the continents, you are all apart from one of the technologies, which is changing the albedo of the deserts. You actually do not get much of a change in precipitation. So a lot of the precipitation changes do occur over the ocean. And this just does show you a diagram of those precipitation changes. And you can see they all have different geographical patterns. And that you can also see, perhaps, you get the bigger changes occurring over the oceans. What I do now want to do with these patterns of precipitation, I do now want to use them to ask a particular question. And I do think this is the crucial thing which makes our results look different than Jim's or David Keith's or the other results you've seen today. And what I'm going to ask with this question is, if you do take the technologies to try and offset the surface temperature change over this period, how does the precipitation climatology change compared with the climate of today? And the important thing is, the way we assess what the climate of today is we take a 500-year control simulation provided by Scott Osprey and the Spice contingent. So what they provided us with was a 500-year control. And we take distinct 20-year chunks of that control to calculate the internal variability in the precipitation climatology. And this is the result you do get when you ask that question. So what these diagrams compare is the precipitation over, what they show is the precipitation over this time period compared to the climate of compared to the climate of today. And what you can see on this diagram is that over a large chunk of the surface area, the precipitation is within this two standard deviations of what we have for today. But for all of these simulations, and it is particularly pronounced for the change in the desert albedo, you can look to see there are significant areas where you get changes that are outside of the climate of today. So today you see patches of red area, you see patches of blue area. The red areas are big increases in precipitation, and the blue areas are decreases, and they are quite significant. What I want to say about the geographical patterns of precipitation is that, to get back to what Phil Rass was talking about today, is that not all model results can be perfect, but and what I would say that I think if we were to repeat these simulations with a different set of model results, we're probably to find that the geographical patterns will look distinctly different. But what I would say, whatever simulation we did, we will probably find that there were parts of the world that had statistically significant look at how they changed from the RCP 4.5 scenario we were comparing with to begin with. So what I do with these precipitation change patterns is borrow from an idea by Angus Ferraro, which is we look at parts of the world where they are insignificant, where the change is insignificant compared to what was happening in RCP 4.5, where the change was effectively returned by the geoengineering technology back to today's climatology. And we looked at where the SRM did try and return it to today's climatology, but didn't quite go back to today's climate. But we also look, try and identify parts of the land surface where the SRM technology did make it significantly worse compared to today's climate. So significantly wetter or significantly drier. So, and this is what the plots do look like when you run them through this algorithm. So what you do find here, over much of the land surface, the changes are pretty insignificant. But you certainly do get significant areas where the rainfall changes are pushed by the geoengineering outside of what we are experiencing today, or what the model is experiencing today. So you get damaging wetting and damaging drying areas. So what we simply did with this, we turned them into areas of the world, we turn this into areas of the world affected by population. So you do, for all the SRM technology, get significant areas where the SRM technology does push the rainfall, make it worse. So, and these areas are larger than where it improves the rainfall. So you can see that some, like the desert wonders, have a very significant effect on a large surface area, but you can look at all the technologies. And I think if you were to repeat the same thing with different GCMs, you might get very different rankings, but you would still get significant populations affected by these technologies. When we presented this before, we were asked to compare our results to GMIP and the other results presented earlier today. And we tried to identify why our results appear to be different. Because if you hear people this morning, they were suggesting that there really weren't big effects on precipitation. And I think it comes from the way you assess the standard deviations. If you look at the way that Ben did in his publication, he compared the 20-year average across different models to the annual average standard deviation across all models. So if you look at his standard deviations, they don't appear to be a bigger than one we discover. So I think by doing that, he's asking a different framing than what we were asking. So just to put up my conclusions, okay, we compared SRM techniques in different climate models for the first time, and I just think how you interpret your precipitation response does really depend on what framing question you're asking to begin with. And we find that our SRM technologies, they all, for a significant portion of the world population, will push the climate out of what we observe today. And just to compare that to, and in terms of the climate impact, I mean, of course you have to compare that to the benefit of the surface temperature change. So the technologies all do a massive improvement in terms of their surface temperature responses. So as people talked about with your NPP, perhaps it is still going to be beneficial to deploy the technologies because they do have a beneficial effect in terms of the surface temperature change.
Brilliant.
Okay.
Thanks, Piers. Okay, we've got time for a couple of questions. I'll start with David at the back there, please, and then Andrew can go after that.
Dave, Keith here. Two questions. One is you talked about big impacts of drying, but all you showed was precip. But the way I understand it, E minus P, evaporation and precipitation, both matter. You can't conclude much about drying from precip alone.
Yeah.
Second question is, you kept talking about SRM technology, when I think what you meant was SRM technology used to restore surface temperature.
Yeah.
And you referred to our work, but in fact, the work, say, that Doug McMartin and I have done, we've tried to show in that paper on responsive moderate SRM that you might well not want to restore surface temperature, and you might want to do something more like holding average precip constant. So can you respond to how
Yes.
your conclusions would be different
Yes.
if you looked at drying or looked at a moderate scenario?
Yes, okay, I absolutely can. That's a very good ones, of course. So what I was comparing with, I really wasn't comparing to your most recent work we've done in Martin. I was comparing to the paper that Ken Caldera did show this morning, when you had your different geographical region there and you showed the change in precipitation.
Actually, that paper also shows that the optimal is not the place where you restore temperature.
Yeah, perhaps I can complete that. So yes, so what I'm going to say to respond to that is that, so if you were to do not a complete restoration of surface temperature, practically quite a lot of the geographical areas would turn insignificant. What I do think is that whatever you did with this one, you would still have significant changes, but the rest of them will be insignificant pretty much everywhere. Did you ask a different question as well?
What about the question of drying versus?
Oh yeah, drying. I think that was just wrong choice of wording. I think this work is just about precipitation. Plus, results would look quite different if you would take the evaporation and the runoff things on top of that. You might get significantly different results then too.
Excellent. I think we've shifted from Andrew to Jim in that corner, and then I'm going to take Stephen's question, and that'll be it, I'm afraid, for this. I'll have to go for coffee. So, Jim? Yeah, I mean, I agree with you that there's that how you frame this question is very important. I mean, what we were showing, and we've shown it from the same model, is if you look at something that people care about a bit more, like net primary productivity, you get a tremendous benefit from solar radiation management. And you get a benefit from solar radiation management compared even to your RCP scenarios. I notice you've backed off on your sort of statements of this is going to be detrimental to, was it 60% of the Earth's population or something that you quoted at SPICE. I just feel as though the framing issues need to be very, very thoroughly explained, if you like.
Yeah,
whenever we're making these statements.
By putting this up as Jim with David, he hasn't quite talked yet, in fact. But what I would say, Jim, and it really answers your question too, is that I have probably framed this more accurately than anybody else has today, because I put up a precise thing I was investigating. What I said I was trying to restore the surface temperature to what it was today. And I was just looking at precipitation climate defined in this particular way. I define it. I think when a lot of people present their work, when you presented your work, for example, it wasn't really completely clear what framing people put in their talk. So when people present their talk, I'm perhaps guilty of it to anyone, but I think we have to be very clear when we talk about our results, what is the framing we compare with. So when David presented results, he says, we're only doing this little bit of geoengineering, and that's okay, but you have to be really explicit about what those framings are. And I think we need to prove as a group of researchers about really defining what we really mean by results.
We're going to take our last quick question.
UVB radiation. I link the exposures of the population to each of these three factors to mortality using concentration response functions. The concentration response functions, or CRFs, that I've used were taken from the epidemiological literature. The first is that an 11% increase in cardiovascular mortality per 10 micrograms of meter cubed of PM2.5 that exposed to. And that's based on a paper by Hoek in 2013, which looked at concentration response functions from studies throughout the world. I link the exposures of the population to each of these three factors to mortality using concentration. Sorry about that, I didn't need to repeat myself. The second function is the rate of change of respiratory disease with ozone, so a 4% increase in respiratory disease mortality per 10 parts per billion. A sulfate-like aerosol with no chemical sources or sinks. This allows me to calculate the amount of that aerosol that falls to the surface in the absence of sulfate creation or destruction without any feedbacks. I then inject, in another simulation, a chemically active tracer, sulfate with sources and sinks, and calculate the photochemical production or loss of ozone and other aerosols throughout the atmosphere. And this results in an optical depth of 0.08, which will be important in a minute. For temperature, I take the 3D monthly mean temperature response from Canny SM2, and it's actually scaled with an optical depth of 0.0094 and calculate the sensitivity throughout the model. And for precipitation, I use global net change, again from Canny SM2, responding to an optical depth of 0.0094. To then unify all of these sensitivities into a single response, I take the simulated results from 1 teragram of sulfur per year injection with the inert aerosol. I take the simulated response with the non-inert aerosol, which results in a 2.4 teragram of sulfur burden. We're using an idealized log normal aerosol with a radius of 0.16 micrometers. I scale the response to temperature by the ratio of optical depths between the temperature perturbation in the climate model and the optical depth in the UCX, resulting in a 1 Kelvin cooling from 2.4 teragrams of sulfur in the stratosphere. And similarly for precipitation, I find a 2.4% reduction in precipitation due to this particular strategy. So I'm now going to describe the number of mortalities that we predict in 2040 as a result of each of these 4 drivers, starting off with the meteorological driver of cooling. So lower temperatures mean slower cycling with nitrogen oxide, nitrogen dioxide, and hydrocarbons. That slower cycling, particularly in urban areas, results in lower ozone mixing ratios and therefore a reduced rate of mortality due to ozone exposure. And we find that in 2040, using UN population estimates for the surface population distribution and magnitude, this results in 45,000 fewer premature mortalities due to ozone exposure in 2040. The PM 2.5 response is a little more complex. In South America, for example, a lower temperature, note that red in here means a positive correlation with temperature, a lower temperature or a cooling results in reduced biogenic emissions and hence a positive sensitivity of PM 2.5 to temperature. However, throughout the rest of the world, and most importantly in South Asia, as temperatures fall, nitrate aerosols increase. This is because ammonium nitrate, which is a volatile and extremely abundant anthropogenic aerosol throughout the world, will actually shift towards the gas phase at higher temperatures. As we reduce the monthly mean temperatures, more of that aerosol is shifted towards the aerosol phase and exposure increases. Note that this is also particularly sensitive to your choice of background emissions. If there isn't NOx or ammonia to form these aerosols, you won't get formation. So that cooling, that reversal of global warming, results in 69,000 additional premature mortalities per year, greater than the ozone benefit. Finally, there's a small disbenefit due to UV exposure, where essentially the loss of tropospheric ozone results in more UVB reaching the ground. And this cooling, this negative global warming, results in 24,000 net additional mortalities per year. Just to clarify, the error bars that I'm showing here are due to uncertainty in the CRF, rather than uncertainty in the model or any other quantification. Precipitation only significantly affects PM 2.5 concentrations, at least at the surface. The reduction in precipitation expected to be the result of 1 teragram of sulfur per year results in a negative, results in a positive impact on PM 2.5 concentrations. And there are 14,000 additional mortalities per year due to additional PM 2.5, modeling only the global net response to precipitation. This is not local or regional responses to, of precipitation. In terms of the injected material itself coming to the surface, of course, the injected material, even though it was injected at the low latitudes between plus and minus 30 degrees and at 20 to 25 kilometers, the same as in the Piers et al. Paper from 2010, the material spreads throughout the stratosphere and settles at all latitudes. However, it's efficiently removed by washout. As you can see in this plot, by the time that we're within about a kilometer of the surface, or well, half a kilometer of the surface, almost all of that material has been removed by precipitation above the surface. We find that if you inject that 1 teragram of sulfur per year with a distribution the same as modern day sulfate emissions, it results in a 26 times greater exposure than if you inject it into the stratosphere. However, that small surviving fraction is still enough to cause 3,900 additional mortalities per year due to increased PM 2.5 exposure. And this is without accounting for any chemical feedbacks. This only accounts for wet and dry deposition of that aerosol. Finally, I'm going to get on to those chemical feedbacks. So injecting between 20 and 25 kilometers, most noticeably, results in large-scale destruction of ozone between about 10 and 20 kilometers in the lower stratosphere. In spite of the reduced CFC emissions predicted in the RCP 4.5 scenario, the increase in hydrogen, chlorine, and bromine-related catalytic cycles, or HOX, CLOX, and BROX, result in up to 25% destruction of ozone locally. At higher altitudes, between 20 and 30 kilometers, there's actually a countering effect. N2O5 in the stratosphere, which would usually be broken down to result in NO2 and NO, which would go on to take part in catalytic ozone destruction, become sequestered on the surface of those aerosols into HNO3, which is a relatively long-lived reservoir gas in the stratosphere. And therefore, NOx, catalytic destruction of ozone in the mid-stratosphere, which would usually be the dominant cycle, is slowed down. And there's a small bounce back and therefore an increase in ozone at these higher altitudes. However, the net effect is to decrease the ozone column by 5% globally. Since the stratospheric ozone has been depleted somewhat, this means that there's actually less ozone in descending air masses. That stratospheric-tropospheric exchange is no slower or no faster in this model, but the ozone taking part in it is reduced. That means that there is less ozone at the surface as a result of stratospheric-tropospheric exchange. This depleted stratospheric ozone results in 24,000 fewer mortalities as a direct result of ozone exposure in 2040. And actually, the reduction in ozone also means 1,100 fewer PM2.5 related mortalities due to slower nitrate production, where the ozone would usually take part in converting NO2 into NO3 and then onto nitrate aerosol. However, of course, the more explored side effect of ozone depletion in terms of human health is UV. The loss of stratospheric ozone results in 3,200 additional melanoma mortalities directly as a result of increased UVB exposure. Noticeably and surprisingly, this means that there are fewer premature mortalities worldwide due to UVB exposure from ozone depletion than there are prevented due to the change in ozone exposure. However, this doesn't take into account things like changes in non-melanoma skin cancer mortality and incidence. The summary is that the net impact of sulfate aerosol injection in this model is to incur 24,000 additional premature mortalities per year. Although I'd like to highlight that even only accounting for the uncertainty in the CRFs, the 95% confidence interval on this is minus 24,000 to 69,000 mortalities. And there's a 24% probability of a net decrease in mortality based on that CRF uncertainty alone. Some other sources of uncertainty which I haven't addressed include these meteorological feedbacks, model uncertainty, and assumptions. And this is only a linear scaling approach, but I'd like to point out that what I've done is highlight what the most important, or at least what I think the most important sensitivities are out of these four. In summary, the reductions in temperature, which are the goal of most stratospheric aerosol injection scenarios, dominate the impacts in terms of health impact due to increased nitrate formation with a partial compensation due to decreased ozone exposure, with a total estimated mortalities of 24,000 per year as a result. The direct impacts of sulfate aerosol injection, by which I mean the transport of that sulfate to the surface and the photochemical impacts of sulfate aerosol injection, are small relative to the potential impacts of these meteorological changes on surface air quality and UVB alone. And future investigation of health impacts should probably focus on these meteorological feedbacks. The only exception I'd point out, again, is skin cancer, where I would say that further investigation is required, especially to enhance these concentration/exposure response functions beyond their relatively crude current status. Thank you for listening. I'd love to take your questions.
Okay, that was a fabulous talk. I'm going to start with a question on this side, and then I'll get to Ken. So it's Phil first.
Hi, Sebastian. One of the figures which I showed for 10 seconds or 20 seconds this morning was a figure from Simona Tilma's work on attempting to assess ozone changes and UVB at the surface with the NCAR model and with a relatively comprehensive stratospheric chemistry package. And the conclusion there was that there was a reduction in ozone at high latitudes and consequently an increase in UVB reaching the surface at high latitudes, but the sign was opposite in the mid-latitudes and tropics. And I wonder whether you can explain the difference in the signatures there.
So I know the paper you're talking about, and my understanding is that they potentially did not account for some very short-lived bromine and chlorine species projections, which will not fall off with the RCP 4.5 projections. I think I'm about to be countermanded.
They certainly did account for many of those reactions. Whether they got all of them or not might be a topic for further discussion.
Certainly. So I suppose what I would say here is hedging it a bit. My understanding is that a later paper found that there's an extreme sensitivity to the exact projections of those VSLs, and that the sign of the change is dominated by those VSLs because CFCs fall off so much. So I haven't investigated it specifically here, but my expectation would be that I have higher estimated VSL emissions in the year 2040 than they do.
Excellent. Go to Ken.
Thanks for an excellent talk. Just to put these mortality numbers in context, do you have any idea how this number compares with, say, the number of current deaths due to the coal industry?
So I can't speak to the coal industry specifically, but I know that three studies in particular, so one by Annenberg et al., one by Silver et al., and another by Lim et al., used the exact same techniques. So they used typically the Jarrett ozone CRF, and then usually a slightly older, more US-specific CRF for PM2.5. And they found that anthropogenic emissions, maybe not the coal industry specifically, result in something like 3 or 4 million premature mortalities per year, compared to these numbers of tens of thousands. What I would say is interesting, and the reason that the meteorological feedbacks need so much investigation, is that Silver et al. Also looked at what past climate change has resulted in, outside of just changes in the surface concentrations due to emissions, and found that the models disagree significantly, but they could find between minus 100,000 mortalities and plus 40,000 mortalities as a result of those past climate changes.
I think we're going to have to move on because I think we've got Ben. Is that right, Hugh? Have we? We think we might have Ben. Brilliant handling of the questions, and a couple more people were interested over there, and Angela, I'm sure we'll catch you at dinner or something. Okay, well done, Seb. That's really good. Any other questions?
You can see SRM impacts on hydrological cycle on the screen. Is that correct?
That's correct.
Okay, so we're now going to go live on our big screen here.
How are we going to do is, we're going to put a mic on the computer? Is that what we're going to do?
Yeah, sorry?
We're going to put a mic on the computer.
No, well, there isn't a mic to go on the computer, but you can speak, you just have to speak to here. But his sound will come out.
His sound will come out.
But the only microphone I've got for going in is, I don't have a mic for going on.
Okay.
Can you try speaking?
Yes, can you hear me?
Yes, we can.
Okay,
all right. Okay. So Ben Kravitz, talk on SRM impacts on the hydrological cycle. Take it away, Ben.
All right, thank you, Neb, and my apologies for the technical difficulties. I promise it worked yesterday when we tested it. So I'm going to be talking about SRM impacts on the hydrological cycle, as you can see from the title. So, of course, I have quite a few people to thank, many of whom are sitting in the room there, and really many people who aren't in the room. Thanks to everybody involved with GeoMIP. We couldn't have done this work without you. So I wanted to talk a little bit about the motivation, why the hydrological cycle. So this is a paper published by Alan Robach and colleagues in 2008, looking at June, July, August change in precipitation for a tropical injection of 5 megatons of sulfur dioxide per year into the lower stratosphere. It's a very similar experiment to GeoMIP's G4. And what I want to highlight is that region there. So you can see a lot of brown, a lot of reduction, and that's we attribute that to a reduction in the monsoon precipitation from geoengineering. And so this caused us to think a little bit, maybe this is something serious that we really need to look at. And that I would say the hydrological cycle was one of the founding motivations behind why we wanted to do GeoMIP. So, and it's not just model results, there are analogs as well. So this is a paper published by Kevin Trenberth and Igwo Dai in 2007, looking at how the global hydrological cycle was suppressed by the stratospheric aerosol loading due to the Pinatubo eruption. So you can see that gray shaded area there, that's the region that was affected by Pinatubo, and both continental discharge and land precipitation went down. So this is also very suggestive because we have some model-based evidence and some actual observational-based evidence. So what does this say about geoengineering? And here are some things we know from GeoMIP experiment G1. I'm sure you've seen a lot of that today, probably while I was asleep, but just in case, the G1 experiment is down at the bottom left. So against an abrupt increase of CO2 from pre-industrial, the solar constant in models was reduced to compensate the net radiative forcing. So you can see these plots here. On the left is 4 times CO2, June, July, August precipitation. And on the right is 4 times CO2 plus geoengineering, also June, July, August precipitation. This is an IPCC figure, so the stippling indicates where the models agree on the sign. And you can see, for one, they agree in quite a lot of places. And also you can see that in the 4 times CO2 run, there's an accelerated hydrological cycle. This is fairly well known. And in the 4 times CO2 plus geoengineering one, there is a suppressed hydrological cycle, especially in the tropics. And this is a robust model finding. And now I want to show you that it's not just that if we aggregate these precipitation patterns. So there are 3 general boxes here. The left box shows global average precipitation. The middle marked GMI shows global monsoon index, and the right is the intertropical convergence zone. So the first 2 boxes in each of the larger areas show an increase in precipitation due to an increase in CO2. So that's the 4 times CO2 run. And the 2 right box and whiskers in each of the sections shows the response of G1. So you can see that the hydrological cycle is accelerated by 4 times CO2, and then it's decreased in G1. And that's not just true for global precipitation, that's also true for the global monsoon index. And actually, if you split the global monsoon index into individual monsoon regions, you see a similar result for all of those. So that was the mean precipitation. We can also talk a little bit about extreme events. So this fairly complicated plot shows a change in frequency of precipitation events. So if you look at the x-axis on the left, you have very small precipitation events, and on the right you have very large precipitation events. So the 4 times CO2 run shows a pattern that's been coined, the rich get richer and the poor get poorer. So effectively, areas that are receiving a lot of intense precipitation events would receive even more under high CO2, and areas that are not receiving a lot of precipitation events would receive even fewer. And the geoengineering run on the bottom panel reverses that trend. So this is experiment G1 again. So you can see that it actually does reverse the rich get richer and the poor get poorer trend. So now into a little bit about the mechanistic changes behind precipitation. So this is just global average precipitation plots. So, and it's a time series. So each line represents an individual model participating in geomip. So these are the 4 times CO2 runs. And you can see initially the precipitation decreases, and then it slowly increases over the course of simulation. So we actually know something about this, and judging from Ken's title, he may have presented something to this effect earlier. So the initial decrease is called the fast response, and this is a radiative effect. So this is without changes in global mean temperature, or with small changes in global mean temperature, there are adjustments going on in the atmosphere, for example, clouds, lapse rate, things like that. And that causes the initial decrease in precipitation. And then as temperature increases over the course of simulation, you get that increase in precipitation. And so that's the 4 times CO2 run. Here's experiment G1. So we effectively get a sustained fast response due to suppression of temperature-related feedbacks. And I put this quote up here. I forget where I found it, actually. I need to remind myself of the citation, but essentially what it says is, if radiative fluxes change, then precipitation must change in a way so as to balance the total column energy budget. And I really like that because it tells us that we can look at these precipitation changes, and if we understand how the energy is changing in the atmospheric column, both at the surface and at the top of atmospheres, the entire column, then we can actually understand a little bit about why precipitation changes. So I'm going to show you a couple of complicated plots here. I've skipped a lot of the math behind this, but basically what you can do is you can decompose precipitation changes in energy units into 2 terms. So the top panel is the mean evaporation term, and the bottom panel is the moisture convergence term. So basically, if you want to describe precipitation at any given point, precipitation can change vertically or it can change horizontally. And that's basically what these 2 terms represent. So this is an average over the first year of changes in the G1 experiment. And what you can see here is that land and ocean precipitation decrease. And if you look at the top panel, so in these two panels, stippling denotes where the models do not agree. It's different from the IPCC convention. And so you can see there are a lot of areas, especially the stronger areas in the top panel, that are not stippled. That means that the models show it's a robust feature of the models to show that precipitation decreases due to a decrease in mean evaporation. Now on the bottom, basically the entire figure is stippled except for a couple of small regions. So what we're interpreting that to say is that contributions from moisture convergence are in most areas small, except possibly in the tropics. We still haven't attributed a mechanism to that. Now, what we can learn further from this is that changes in moisture convergence, at least by this mechanism, are largely due to changes in mean circulation. So the Hadley cell, the Ferrel cells, things like that. So this suggests to us that changes in circulation in experiment G1 are small. We have not verified this because we're a little bit undermanned. There are quite a few studies to do. So if anyone out there is looking for something to do in terms of analyzing GeoMap output, we would really appreciate your help if you want to look at some of the circulation changes that are going on. So now I want to talk a little bit about some uncertainties in our results. So here are plots of the Bowen ratio. And these are fairly complicated plots. So I'm actually showing you ratios of ratios. And just to make it a lot easier on you, I've given you a cheat sheet. So if you look right below the color bar, you can see that I've said that land values greater than 1 means that it's drier than in the control simulation. And if land values are less than 1, it means it's wetter than in the control simulation. So on the left, we have the results for the 4x CO2 run. And on the right, we have the results for the geoengineering run. And what you can see from these is the patterns on there are very similar. And what it took us a while to figure this out through a couple of idealized simulations, but what we figured out is that a lot of this is due to the CO2 physiological effect. So both of these take place in a 4x CO2 world, and plants use water more efficiently when there's high CO2, so they close their stomata, and this reduces evapotranspiration. So that's one of the large effects here, we think. Now, there was one study done by John Fife and the Canadian group, and they actually picked a lot of these apart in their model, and they found that the CO2 physiological effect represented about half of the surface energy budget effect in their model. So clearly this is something that needs to be quantified a little bit better. So here's a plot from a paper by Ulrika Niemeyer, where they looked at a few different methods of doing geoengineering in their climate model. So for those of you who are familiar with experiment G3, all of these are based on that. The overall goal is against RCP 4.5 to keep radiative forcing at 2020 levels. So salt is the injection of salt into the marine boundary layer. Fix is where they just fix the radiative forcing. Sulf denotes stratospheric sulfate aerosols, and sol indicates a solar reduction. So what this is plotting is changes in evaporation over in the entire simulation. And as you can see, the results really depend on how geoengineering is done. So a lot of what I've just talked about is experiment G1, where you increase CO2 and turn down the sun. That can tell us a lot, and we've gained quite a lot of knowledge from that, but clearly, from this figure at least, that cannot tell us everything. There are a lot of things that are particular to sulfate aerosol injection that solar reduction cannot model. And of course, the results of sulfate aerosol injection are likely strongly dependent on how aerosol microphysics are represented. So there are two important messages here that I want to talk about in terms of my results. So number one, so if you look at this plot, on the bottom is precipitation change, and on the left axis is temperature change. The origin here is the pre-industrial control. So if you look at the distance between the origin and the 4x CO2 run versus the distance between the origin and the G1 run, that I've circled there, you can see that the geoengineered climate looks a lot more like the pre-industrial climate than the 4 times CO2 one does. And the reason I bring this up is I think it's important when you are talking about geoengineering to talk about what your baseline of comparison is. This is not a new concept. I'm sure people have talked about this this morning, but it's worth reiterating insofar as it's important to take this into account when interpreting the results I've presented. Another point that I wanted to make is that experiment G1 it implicitly assumes that geoengineering is the only response to an increase in CO2, which is really useful for idealized experiments and figuring out how the climate system works, but that doesn't, in my opinion, that doesn't really make sense in terms of how geoengineering might actually be used if society should decide it wants to use it. So the results I've shown are in the circled area there. And this goes to a point that David was just making in the Q&A session earlier. There are many possible climates that could result from geoengineering depending upon the amount of geoengineering. So in theory, one could travel anywhere along that line. So the example that I heard was maybe no precipitation change and a little bit of increase in temperature, or maybe just go slightly down those lines with just a little bit of geoengineering. So that brings up another point, that the hydrological cycle results are highly dependent upon the amount of geoengineering. Here's a paper by Jim Haywood showing some initial steps in looking at multiple degrees of freedom in geoengineering. So what he did in his study, which he may have already talked about, so apologize for the repetition, is looking at geoengineering just in the northern hemisphere or just in the southern hemisphere. And this is geoengineering with stratospheric aerosols. So the top panels are precipitation and the bottom panels are net primary productivity. And depending on which hemisphere geoengineering takes place, you can get a shift of the ITCZ, and that really affects precipitation in the Sahel. So if you look at northern hemisphere geoengineering, there's a drying of the Sahel as measured by net primary productivity change. And if you look at the southern hemisphere geoengineering, there's a greening of the Sahel. And so that leads me to some additional work that we have done looking at sort of a range of possible outcomes. What if there were multiple degrees of freedom? So in the top left panel, we looked at different latitudinal patterns of solar reduction. And in the bottom left panel, we looked at geoengineering in different seasons. And so if you look at the right panel there, this is showing, the shaded area shows sort of a range of achievable climates if one were to look at different combinations of these different methods of, or these different degrees of freedom in terms of geoengineering. I'm not assigning a value judgment to any of these. I am not saying anyone is better than the other. What I am saying is that by only concentrating on experiment G1, you're missing a range of possibilities of geoengineering. It's not just geoengineering on or geoengineering off. There are quite a few degrees of freedom here. So that leads me to my conclusion slide, sort of a whirlwind tour of things we know about the hydrological cycle. We know some things about the hydrological cycle effects of solar reduction, and we know some things about why those effects show up in climate models. That said, there are a lot of things we don't know, especially about other types of geoengineering. And the hydrological cycle effects are not always the same as for solar reduction. The CO2 physiological effect needs to be further quantified, and according to a lot of studies out there, it could be very important. A lot of climate models represent the CO2 physiological effect. I am not a land surface expert, so it is not for me to say whether it represents those processes well. Also important to note, so my title was SRM Impacts on the Hydrological Cycle, which when I said impacts, that may have been the wrong word to use because hydrological cycle changes are not impacts. So for example, I can talk about precipitation, I can talk about evaporation, but that does not necessarily say anything about things like regional water scale.
I didn't do that. No, I didn't.
Engineering is done. That is, there are multiple potential degrees of freedom. So I think that's all I've got, and I'm happy to take questions.
Brilliant. Thanks, Ben. full screen. Ben, can you switch us over so we can see your face rather than your slides, or that might be nice.
I can try.
Make it full screen. Oh God. Oh no. Okay, full screen. Oh, I can see and your slides. Brilliant.
Good.
Okay, great. Sorry, that's my face. Okay, do we have a couple of questions for Ben?
Oh.
We're seeing a lot of you. Yeah, there we go.
There we go.
Yay! So, any questions in the room? Go on, we've managed the technological feat of excellent up there, of getting Ben via Skype. So, ask the man a question.
A bit of an offbeat question. It's hard for me to imagine a world of 4 times CO2 as being a reasonable comparison. It's so far beyond anything we know. I cannot see what's particularly reliable about the models, and it's really a world that I know we can get there, and maybe we're going there, but it's so far beyond what's manageable. Why bother?
Ben, did you hear that?
Not very well. Would you mind repeating it?
Doesn't make any sense anyway. I just said, why bother examining a 4 times CO2 world? I mean, it's useful, I know, but it's the consequences of the massive change in climate are so far beyond comprehension. It's difficult to know why we should pay attention to detailed modeling.
Did you catch that? So, why use a 4 times CO2 world as a comparison when your 4 times CO world is so far ahead? It's a massive amount of CO2, and it's a trajectory we're possibly on, but not necessarily. So justification for 4 times CO2. Go.
Yeah, that's a really good question. So the way I see it, it's really hard to come up with a climate model experiment that is so simple we can't learn anything from it. And those simple experiments actually have quite a bit of value in teaching us how the climate system works. So we liked the experiment G1 because it was very easy for all of the models to do. So we got quite a bit of participation. We now have 13 models that have participated in it. And also, it's not as inapplicable as you might think. So there are a few papers out there by Peter Good, who's been looking at just how applicable the 4 times CO2 runs are to, say, RCP 8.5. And there are clever ways in which you can scale those results to get something meaningful about, say, more realistic simulations.
Okay, that's brilliant, Ben. I've got one final question, I think, or I think people might be ready for dinner. Sorry, Ben. Thank you so much for your patience. So thanks so much for round of applause, final applause for Ben, for Sebastian, and for Piers and your questions. Thank you very much.
Thanks.
Thank you.
What?
Thanks everybody today for an excellent day. I've got nothing to say. Are there any questions anyone have about this evening? Everyone knows what they're doing. Be at Lady Mitchell Hall for 7 o'clock. Go to the pub. The talk starts at 7:30, but we need to be in the room by 7:15. It says 7 on the website, on our website, or the